नहीं, मैं तो पहले से ही
introduce
कर रखा है.
session, and I hand over this session to Professor Brijesh Kumar from JNU to chair this session.
Okay, thank you, Manoranjan, and all the other organizers for asking me second time to do this. I mean, I've already done the chairing for the last session, but I'm happy to chair this session again. I mean, also. And in this session, we have, which is also the last session of this wonderful conference, which has been going on for last 4 days. This is the 5th day. In this session, we have a total of 5 talks, and of which the first 2 talks, in fact, first 3 talks are 30 minutes each, and the last 2 talks are, I think, 15 minutes or so. So the first speaker for this session is Ujjwal Sen from HRI, Allahabad. And he will talk about quantum devices in systems with impurities. Ujjwal, you have 30 minutes, and I'll remind you at 25 minutes.
Yes, yes, yes.
So, yeah, we can start now, please.
Yes,
yeah.
Yes, yes. So, yes, thank you, Brijesh, for and the other organizers for this opportunity to speak in this thing. In this wonderful conference. Yes, so I'll be speaking about quantum devices in systems with disordered parameters and impurities. I'm from HRI in Allahabad. So yes, so quantum devices are known to be useful. And some examples are quantum computers, quantum crypto devices, and others. And some of them are in the market, some are not. And many, though not all, run with the resource as something called entanglement. So I will give a sort of a hand-waving definition of entanglement before starting off with the main talk. So let us think of 2 worlds, one with small letters and other with capital letters. And let us consider this expression. Can you see my cursor? I hope you can see my cursor, no? Yes. So, yes, yes, yes. Thank you. Yeah, thank you. So look at, if you look at this expression, so this expression, every term has a first letter that is small and a second letter that is capital. And this expression is one which can be factored into like this, into smalls and capitals. This all of us have learned in school. And there are, of course, much more complicated ones like this one, which can also be factored like this one, which into smalls and capitals. But there are also expressions like this one, which cannot be factored into an expression of small letters and an expression of capital letters. This simple fact, we all know this fact from school. However, this simple fact, when carried over to tensor product Hilbert spaces, provides entangled states. Well, this is my definition of entanglement. This, of course, is not a complete one, but I just wanted to have a quick and general one. Such entangled states can and has been prepared in several physical systems around the globe. And what is interesting is that they can be useful. The other part of this, so the other link of this talk is impurities, and whether we like or not, they are everywhere, as we all know. And the point is that there are recent attempts and successes of preparing artificial materials in which one can engineer impurities. I don't pretend to know how they do it, but I know that they do it. And so why this is done, and why are impure systems important, and why people even try to artificially create such things? Well, creating disordered systems leads to having controllable impure systems, and for example, it makes the study of phases of such systems easier than in other systems. And impurities also can sometimes, though not always, be useful. And we will see some instances how they can be in this talk. So the topics that I hope to cover are these two topics: glassy disorder and quantum random walks. I will tell you, I mean, many of you already know what is glassy disorder, but I will still, for completeness, tell you what is glassy disorder. And the same goes for quantum random walks. And then I will try to cover a second topic about Nogo theorems and disorder theorems, the disordered systems. Well, I have some more topics down the line, but I don't think I will have time for that. Time for those. So the first topic. Well, this is a cartoon, of course. So we want to help Johnny Walker walk home. So what does it mean? So we are thinking of a drunk who is trying to reach home. Why is she or he drunk? We will come to that in a few minutes, in a few seconds maybe. So the first thing about the drunk is that he or she is trying to reach home, and she is taking discrete steps. And she is doing that on a one-dimensional lattice. And at each steps, there are two options. So either, because it's a one-dimensional lattice, at every point, you can either go to the left or to the right. And she does it randomly, and that is the reason we call this person as drunk. And to decide on which way to go, she tosses a coin at every site to decide in which direction to go. Now, if you have a classical walker and a classical coin, the walker never reaches home, in the sense that the position distribution of the walker is the Gaussian one. Yeah, so this is what I say. And to be more specific, if you consider the variance of the classical walker's position distribution, the variance is proportional to the square root of the number of steps. But, and this is what we want to show, is that quantum mechanics helps. In the quantum case, the walker does reach home, in the sense that if you consider the variance, this sigma is the variance here, this sigma. In the sense that the variance is now proportional to the number of steps. It was the square root of the number of steps in the classical case. Here it's the number of steps. This is not my work, this is by other people. I have not given the reference here. The difference with respect to the classical case lies in the coherence in the coin, the quantum coherence in the coin, the quantum coherence in the walker, and because of the entanglement between the coin and the walker. So what we wanted to see is, what if there's disorder? And there are different ways in which disorder may appear, and many people have considered this. Here we consider a randomly distributed number of steps after every coin toss. The disorder is, and this disorder is assumed to be quenched. So let me digress for a few slides to define what is quench disorder, just to be complete. And so let me just go to the next one. I mean, impurities can come in many ways, and one of them is this quench disorder. And this is also called glassy disorder. And the main point is that this type of disorder equilibrate long after all the relevant observations are over. So the physically relevant quantities in this case are the quenched averaged quantities. And so what we do is that we find the value of the physical quantity for a given realization of the disorder, and then average over the possible realizations. There seems to be some comments.
No, it's okay. Please go ahead. I don't see any comments in the chat box.
Okay. So so this is what I'm saying. So these averages are so in a quenched disorder system, it's the quenched averaged physical quantity that we will be interested in. And so in this quantum random walk, we will be interested in a quenched averaged variance of the walker. Yeah, so still remaining with quenched averages, I just wanted to tell you that what does it mean by this. Suppose there is a neighborhood in which I want to find out how many girls play football in this neighborhood. And this observation, because this is a big neighborhood, it will take some time, maybe let's say a few weeks. But during this week, the number of girls who is interested in playing football or does play football will not change substantially. So this is the meaning of what I mean by a quenched disorder. I mean, this is of course a cartoon again. And now we considered a Poisson distributed disorder of the number of steps at each coin toss. And this is the plot of it, where this is the quenched disordered variance. And this T here is the number of steps. It's usually denoted by T in this literature, in this area. And so the scenario is that after every coin toss, we toss a Poisson coin, which means it's just a Poisson random variable, which has unit mean. The mean is 1. The reason we choose 1, because you remember that in the ordered case, the walker was moving 1 step after every coin toss. So we want to, because we want to compare with the ordered case, we wanted to keep this as a unit mean, and this is the result. And so if we do the algebra, we get the scaling factor that we get is 0.8. So this exponent was half in the classical case and 1 in the quantum. So the disordered quantum is somehow in between the quantum and the classical ordered cases. And so it is super diffusive, but sub-ballistic. So, well, I mean, quantum mechanics does help, but I mean, not a lot, because there could be disorder in the system, which will finally maybe reach home, but maybe not so fast. We changed the mean of the Poisson distribution. The scaling exponent did change a little, but not a lot. We changed the distribution. We took different types of distribution. In this case, we always took the mean to be 1 in all these distributions, with different types of variances. And again, the exponent was not very much changing. It was sort of remaining the same. We don't claim this to be a universal feature, but we sort of suspect that it could be an universal feature, that this somewhere around 0.8 scaling will remain. But this, of course, we cannot prove as of now. So these are the people who did this. I mean, the pictures are of the juniors, and there is Aditi also in both the papers. So I presented the first paper. I did not present the second one. In the second one, we considered one-dimensional, but on a circle. And this also has some interesting features, but I will not discuss that. So, yeah, so how much time am I left with?
You have enough time, at least about 17 minutes.
Pardon, once more?
Sorry, you have about 17 minutes.
17.
17, yeah.
Okay. So I will go to the second part. Yeah. Yeah, so the second part, as I already advertised, is about the Nogo theorems in disordered systems. So, Nogo theorems are an important thing in quantum information and computation. There are several applications that turn up by using Nogo theorems. The most famous probably is the no cloning theorem, which provides us with quantum cryptography. So here we will discuss about two such Nogo theorems and try to see what happens to them in systems with disorder. So this is one of the Nogo theorems that we discuss. Again, let me have a cartoon here. So this is some sort of a monogamy here. We have a three-party system. This is represented by these three people here. And you can show that there is some application in quantum information which is called dense coding. I will not discuss this. It's a quantum communication protocol. And you can show that for every three-party system, either A and B, so these three parties are A, B, and C. You can show that for every three-party state, this is represented by RABC, either RAB is useful for dense coding or RAC is useful, but never both. So, I mean, this is sort of a monogamy of sorts that either you have usefulness in AB or usefulness in AC, or if not in, or in none, but never you can have usefulness in both the in RAB as well as in RAC. Okay. This is with respect to this quantum dense coding protocol, but a similar relation holds for Bell inequalities. So if you have a three-party state, RABC, then either RAB is will violate a Bell inequality, or RAC will violate a Bell inequality, but never both. It can be that none of them violate. So if I have an isotropic lattice of quantum spins, almost always any site pair AB has an equivalent pair AC. I mean, there can be some pathological, people have pointed out that there are some pathological cases where one cannot find an equivalent pair. But in a usual one, you will always find such a one. So for example, in a one-dimensional lattice, if you have A and B as a nearest neighbor, the other neighbor of A will be C, and you will have an equivalent pair. Equivalent in the sense that they will be the same states. And so, because of this monogamy relation that we stated in the last slide, two-side states in such systems are always useless. Useless in this sense that they cannot be used for dense coding and they cannot be used for violating Bell inequalities. So this is an example. So this is, suppose this is a one-dimensional lattice in periodic boundary conditions. And so, well, so the nomenclature here is different. I mean, so I was talking about AB and AC, but so here B is, so in the previous slide, A was a node, sorry for this. A was the node with which B and C were connected. In this, B is the node with A and C is connected by the same thing. So in an isotropic lattice, BA and BC are the same states. And so they will either both violate a Bell inequality or both not. But as we saw, that both violating the Bell inequality is not allowed. So the only option left is that both will not violate a Bell inequality. The same goes for quantum dense coding. So either they will both violate, so because of the isotropic, either they will both be useful for dense coding or none. But we saw that this both is disallowed. So the only option left is none. So what we want to see, whether this status changes if we have a system with disorder. So again, we consider a quenched disorder spin system, one-dimensional, where the disorder is a glassy one, just like before. And what we see is that the quenched averaged observable, so we considered quenched disorder in the interaction as well as in the field terms of several spin models. I have not given those spin models here. These were transversizing models as well as Heisenberg models and XY chains. And in all these cases, in different types of disorder that we put in for the different parameters, we saw that the quenched averaged observables, they can become useful. Now we have to note here that if you consider the quenched averaged observables in these scenarios, although the states themselves are unequal. So for example, if you go to this picture, so here, for example, in a given realization of the disorder, suppose the interaction between these two is J3 and the interaction between these two is J4. But after you average, then average over the disorder of any physical quantity of BC and any physical quantity of BA, they will be the same. The quenched averaged quantity here as well as the quenched average quantity here will be the same. So we come back here. These quenched average observables are again the same, but yet they can sometimes be useful. They're not always, but sometimes we found examples where by introduction of the disorder, this monogamy that was there in the ordered system was violated. And these are the places where we check this. It was the anisotropic quantum XY glass, the random field quantum XY glass, and the quantum XYZ glass. By glass, here I am using the notation that glass is to denote the interaction is disordered. Quench disorder. Yeah, so this is what I'm trying to say is that in this ordered case, these quantities become equal and they are bounded to the classical limit. In the disordered case, the quenched averaged values are again equal. And despite this, the monogamy is violated and we have quantum advantage by, for example, violation of Bell inequalities. These are some curves. So for example, this is for the anisotropic XY class. The anisotropy we took to be 0.5. The field was 0.4 with a constant. And the mean interaction was J bar kappa. And standard deviation of the interaction was kappa. The temperature was 0. We're doing ground state. And these are the different system sizes. And we saw, and this top curve is for the Bell inequality violation, and in the below in this panel, it is for the capacity of dense coding. And in both these cases, we find that there are regions in which the advantage over the ordered case. Yes, so this is the take-home message that I want to say. The monogamy can be sort of fogged by disorder. So, and these are the people who did this work. And sorry, I missed the reference here. This is Devashish, Shadu Khan, and this is Sudipto Singhorai, this is Devraj. And all of them have moved out of the group, and there is Aditi as well in this paper. Well, I will finish here. I will not go to the next topic because this will take too much time. I will just go to the conclusion straight off. So what I wanted.
If you like, you can take time because there is enough time, but it's up to you.
Maybe I finish here because.
Okay, as you feel. Yeah,
I think it's good to finish here. Yeah. So what I wanted to say is that impurities exist, as we all know, and recently they can also be engineered in artificial systems. And such systems are interesting, of course, because they have interesting physical properties. They show nice features, nice phase transitions, and so on. What we wanted to discuss here was that they can at least sometimes be useful. With that, I'll finish. This is the group in which we work. You are all welcome to visit our group. Thank you.
Thank you very much, Ujjwal, for a nice and clear talk. And there is enough time for some discussion. So audience, please feel free to ask anything. Any questions from anybody? I don't see any question on the chat box, so I presume people will ask if, yes, who's there? Somebody want to ask a question, please? Hello. Okay, I have a small question, Ujjwal. In your first part of the talk, you said the exponent alpha, which was 0, I mean 1 and 0 for quantum and classical cases, was always around 0.8, 0.7 for various kinds of distributions. So
Exactly.
that was a bit of surprise to me. I mean, I was just wondering that why is there no distribution dependence on the way disorder influences quantum Walker?
Yes, yes, yes. I mean, I mean, the short answer is that I don't know.
Mm-hmm.
I mean, this we did not understand. I mean, not only that, I mean, even within the distribution, if I change the mean and the standard deviation, that it doesn't seem to, I mean, it does change a little, but not a lot. So there seems to be, it could be that there is some basin of attraction that sort of keeps it within a very small range. But I don't understand it. I don't understand it as
I
well.
mean, just my, I don't know, I have no insight, but maybe the way you are putting in disorder, I mean, it's like you are introducing disorder in some way. That, of course, is a matter of detail in which you are doing calculation. But maybe it is not really severely impacting. So you have to rethink about your disordering strategy. I believe so, because it seems surprising that you are changing distributions in various ways, yet the exponent seems to be stuck around 0.8, 0.7. So one has to revisit the disordering protocol and see what am I disordering and why is it not influenced? Because I can imagine if the disorder is very strong, things are probably likely to become more and more classical.
Yes, I mean, it does become a little bit more classical than the quantum,
That is true. Yeah.
but not a lot.
Yeah.
This is, I don't understand it.
Anyway, there is one another person who want to ask question. Arindam, you can ask the
Yeah,
question.
can you hear me?
Yes, yes.
Okay, good. Ujjwal, thanks for the talk. It's very nice.
Thank you.
I have a probably very nice question, actually, partly to what Brijesh just asked. So when you say disorder, is is this some form of a quench disorder in terms of which doesn't change with time, or say, for example, even can we take decoherence to be also a disorder?
No, so here we have put the disorder that is quenched actually. So, why? What do I mean by quenched here? So, this walker, who has the freedom of moving either left or right, depending on the what the coin gives her. So, if it's a head in the ordered case, if it's a head, she moves left, and if it's the right, she moves. If it's tail, she moves right. One step. In the disordered quantum case, what we did was that when it is head, she moves n steps to the left, and if it is tail, then she moves n steps to the right, and that n is a Poisson distributed disorder, a Poisson distributed random variable, which we take as quenched, meaning that we find out the standard deviation for a particular walk, and then we do this for different realizations of the disorder at every step, and then do the averaging.
Okay. Okay. Good. No, I just wanted to clarify that.
Yeah. Thanks.
Any other question from another person? Just I have, since there is enough time, I have one more question for Ujjwal, which is about this. You know, you were talking about equivalent pairs of AB and AC. Now, so when you say equivalent pair, what you exactly mean? I mean, that was not clear to me somehow. Does it mean, I mean, just let me say what I have in my mind. So if you calculate, if you have a state and if you calculate the density matrix of AB or the density matrix of BC, then if they are same, then you would say they are equivalent, or what is it, the precise sort of?
Precisely what you say, yes. So it's here. So if you look at this place, if you find out the state of AB in, let's say, in some state, the equilibrium state of the entire thing or the ground state of the entire thing, and I trace out everything and find AB.
Okay, so reduced density matrix of AB.
The reduced density matrix. And then I find out the reduced density matrix of BC. They will always be the same because of isotropy.
Okay, so now it's clear to me, and therefore there is a related remark I have to offer. which is, if I understand, you want to sort of uh, beat the no-go problem here and want AB or BC to be individually useful. Uh, for that, you can actually do frustration also, because there can be frustrated situations where, although the model problem is isotropic looking, so AB and BC appear to look equivalent at the Hamiltonian level, but actually the state which system realizes can have AB not equivalent to AC. So I'm saying you don't have to necessarily, I mean, you can try. I'm sure you are probably trying along these lines. That disorder may not be the only strategy. Disorder means the way you are randomizing the couplings. It could be completely non-random couplings, but frustration due to competing interactions. Just a suggestion.
But I mean, if it is an isotropic lattice, even in a frustrated system, these will be equal, no? I mean, this in one-dimensional, this frustration will not appear. But suppose it's a two-dimensional system.
No. In 1D, suppose you have nearest neighbor J's and the next neighbor J's.
Yes, exactly. But
and you can easily arise at a situation where the ground state is AB dimer, but no BC dimer. So the system has spontaneously chosen AB to form a singlet, but not BC.
Okay. In such a system, of course, yes. So if you consider this Majumdar-Ghosh thing, yes, of course.
Yeah, Majumdar-Ghosh, or even other problems, various kinds of problems. So I'm saying frustration can help systems spontaneously develop some sort of, breaking of symmetry.
Certainly. So you are very right. So in this frustrated system that you said in the Majumdar-Ghosh model, where this AB is a singlet and BC is not, that of course is not isotropy. So by isotropy, I mean the isotropy at the state level, not at the Hamiltonian level, because otherwise this monogamy will not work.
Anyway, I'm sure but this was just a remark I had in mind.
But it was a nice comment.
Yeah. So, well, if there are no other questions, then let us thank Ujjwal for a nice talk and move on to the next speaker. Ujjwal, you may undo the screen sharing.
Thank you very much.
And the next speaker is Urvashi Sinha from RRI Bengaluru, and she will talk about quantum experiments using satellite technology. So Urvashi, are you there?
Yes.
Please share your, okay, screen.
So do you see my screen now?
Yes, I see your screen,
great.
and we hear you, and just move around the cursor a bit just to see if your cursor is moving.
You can see it move. Yeah, great. So everything is working in the beginning. So thanks a lot to the organizers.
And I'll remind you at 25 minutes, you have 30 minutes.
Yeah. Okay. So thanks a lot to the organizers for inviting me to speak at QMAT. The topic is quantum experiments using satellite technology. And I realize that this topic may be not something that we have discussed during the rest of the conference. Maybe not too much discussion has happened on quantum communication and quantum key distribution. So what I will do is, in the beginning, I'll give a brief overview of the various types of experiments that we are working on in photonic quantum technologies at RRI in our lab, then go on to motivate the need for quantum communication and quantum key distribution along with our own work on this topic, and then talk about long distance quantum key distribution and satellite-based QKD. So a bird's eye view of our lab activities. This is a snapshot of various experiments that happen as we speak in our lab. So essentially what we do is we work on different types of photon sources. So it's, single photons as well as entangled photons. So this is something, so ours is one of the first labs in India to be working on these applications of photons and making them and applying them to quantum applications, quantum technologies. And this is something, a review that I was recently invited to write, and this may be of interest to people here who may want to know a little bit more about these photon sources. And in fact, while we work on nonlinear optics and spontaneous parametric down conversion, there are other ways of doing this, for instance, including quantum dots and NV centers and so on. And so there's a lot of opportunity, for instance, for the condensed matter community to come up with brighter and better photon sources, as well as detectors for these photons, both in the IR as well as in the telecom wavelength. So this is something that may be of interest to this community. So okay. So just one second. And this is a picture from my lab. This is an example of an entangled photon source. So here you can see, these cones of down conversion, and this intersection point is what gives you the entanglement. So this is what you need to harness if you want to work with entanglement per se. Going on to the various applications and various topics that we have been working on in photonic quantum technologies, one of the key areas that we have been investigating for a long time now is actually fundamental tests of quantum mechanics itself. So there are these various principles of quantum mechanics, for instance the superposition principle, or let's say the Born rule. So these are all forming the basis for the various technologies we are actually applying them to. And so one of our longstanding things has been to investigate how precisely we can trust these principles and do precision tests to kind of bound these things. So here on the left, you see a series of work we have done in which we have found the correction term to the superposition principle, which is necessary when you talk about interference experiments. And in this work here in 2014, we actually proposed how to do an experiment to measure this correction term. And this particular work here in 2018, we actually did the first experiment to measure this correction term in the microwave domain. Another area that we work on is fundamental quantum optics itself. Of course, that is what we do, quantum optics. And so some of these principles of quantum optics, we try to test them to their limits, let's say. And so here you have a homomandrel dip, which is supposed to be a diagnostic for a photon source. And what we have gone on to show in this work here is that we can actually get 100% homomandrel dip using even classical pulses and phase control. In a very recent work, we have come up with a new method of quantum state estimation. So now you know that if you want to estimate the quantum state, you just can't measure it, because if you just measure it, then of course you destroy it. So there are means of doing this which involve usually quantum state tomography. So what we have done and come up with is a method which we have shown experimentally, which is called quantum state interferography, by which we can come up with a much more less resource intensive methodology for finding this quantum state using an interferometer to our aid. And so we can do a single shot estimation of the quantum state of a qubit, as well as the entanglement for a bipartite pure qubit system. And this also scales to higher dimensions in a linear manner. Going on to quantum computing and quantum key distribution, which are also our areas of interest, what we have been doing in this series of work is actually working on what is called higher dimensional systems. So now what do you mean by higher? So usually we talk about qubit-based systems in quantum information. So qubit-based computing and QKD and so on. So what we are doing in our lab is we have come up with a way in which we can do this in higher than 2 dimensions. So let's say 3, 4, 5, and so on. And this has a lot of merit, which we won't get into now. But the idea is that we actually have established in our lab a bipartite Q-trit system using what is called the pump beam modulation technique, which we have invented, by which we have a nearly maximally entangled pair of Q-trits now. And so we've come up with a new measure for this entanglement and also demonstrated that. And now we are working for various quantum gates for the quantum computing applications, as well as QKD using these higher dimensional systems. And in fact, if you wanted to know a little bit more about it from a general perspective, this is an article that I was invited to write, where I have actually given an overview on these higher dimensional work that we have been doing for the last several years. We also work on, of course, measurements per se, and generalized measurements or weak measurements is something we are using as a tool to understand better the evolution of the quantum system between preparation and the strong measurement in the end. And so this is an area in which we have done a lot of work in experiment as well as theory, in which we have been able to come up with interesting things that we have measured, which wouldn't be quite possible using conventional von Neumann measurement. And so this is what is called weak measurements. Of course, entanglement, following on Ujjal's talk, entanglement is of course a ubiquitous source in quantum information, and we are very interested in understanding it better, both the static and dynamic properties of entanglement. And here you have an entangled photon source, and in fact this is the experiment that is almost finishing now, in which we are investigating a property of entanglement called sudden death of entanglement. Now it is as gory as it sounds. So what happens is when entanglement is interacting with the environment, then at a certain point suddenly it goes to 0. And so this is something you do not really want. so what we have come up with is a protocol by which we can manipulate the entanglement sudden death such that it either doesn't happen at all or it happens later. And so this is going to be a proof of principle experiment in using entangled photons. And this can be, of course, then crossed over to the, the solid state systems, the superconducting devices, as well as semiconductors and so on, where you can hold on to the entanglement for longer. Now, going on to quantum communication, this is, of course, the focus of the current talk. This is, the main quantum aspect of the secure quantum communication is, in fact, the key distribution problem, which is called quantum key distribution. And in fact, it is, we can call it the most practical quantum technology, because in some sense, this is the one which has been established in many labs worldwide, as well as companies have taken it up for commercialization and so on. So there is a lot happening in quantum key distribution, which is not just at a either at a theoretical or just at a rudimentary experimental domain. It's actually much more advanced than that. So why should you worry about quantum key distribution? So now, of course, these are all applications like credit card purchase or online banking, polling, electoral polling, as well as defense communication. These are all examples of what I would call strategic communication, where you require the communication to be secure. You don't want a third party to get to know what you are trying to communicate, right? So here in this case, what is currently happening is that this is something which is being made secure using what is called classical cryptography. But the problem is that classical cryptography, and we'll see why, is actually going to be compromised with quantum computers. Okay, and so quantum computers are really knocking at our doors, and so we need to take steps now so that we can prevent this catastrophe. And the solution is also quantum, and that is quantum cryptography. And the problem with classical cryptography is unconditional security is not possible. So what does that mean? For example, you've all heard about the RSA protocol. And so this is based on the mathematical complexity of factoring large numbers. Now, so far so good. So then maybe things are secure. But then comes along Peter Shor, who has come up with what is called the Shor's algorithm, which can use quantum gates and perform factorization in polynomial time. So essentially changing the hardness class from a much harder problem to an easier problem. And so essentially what we think is secure will not remain so anymore. So that is the general idea, that computational resources grow very fast, and a very hard problem could be solved tomorrow using brute force attack. There could be new algorithms for classical computers. Of course, we have quantum computers which will run the short type algorithms. So my security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure. And so this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem. And the most important part here is the key distribution, which is called quantum key distribution. So now if I take an example of the RSA, so this 2048-bit RSA key length is supposed to be kind of secure. And so the idea is that there is a challenge which tells you that it will take 1 billion years with a classical computer. But Microsoft research tells you that a quantum computer could do it in 100 seconds. Okay, and so now take this with a grain of salt though. A quantum computer will employ Shor's algorithm to solve the factorization problem. Okay, but it is estimated that this 2048-bit RSA key could be broken on a quantum computer comprising 4,000 qubits and 100 million gates. And we all know that we are not there yet in terms of the computing. We still require a few more years in order to reach this large number of qubits and gates. But then that doesn't mean we should be complacent now, because there is a lot of research happening, both from the company's end as well as from individual labs and researchers all over the world who are actually making this more and more real. So we already have what is called quantum supremacy, which is a certain number of qubits. And so this is growing very fast. So we don't want to wait for this to actually become available in a few years' time to break our codes and then come up with a solution. So solution also has to come from now, so that it is not even a problem when this actually happens. And that is why quantum key distribution or quantum communication needs to be something in which we need to do a lot of work from now itself, even if the quantum computer which will break that particular key is not quite there yet. Okay. And so how does quantum mechanics protect information? So the idea can be summarized as follows. Well, measurement disturbs the signal on an average. This is to our advantage. Then we have uncertainty principle. So if the signals are non-orthogonal, adversary cannot ascertain which one it is. Then we have no cloning theorem. So we know that unknown quantum states cannot be cloned by an adversary. And then, of course, we have quantum entanglement, where quantum correlations can be used to protect information. So these are all examples of principles of quantum mechanics and ideas in quantum mechanics which are used to protect the information. And there are different approaches to quantum key distribution. You can have prepare and measure based approach, where the security is based on uncertainty principle, and examples being BB84 and B92 protocols. These are popular ones. Entanglement based QKD, where the security is based on entanglement. Here, popular ones are BBM92 and Eckert-91 protocol. So these are different approaches. They have their own reasons for being there. So the BB84 is, of course, the most well-known QKD protocol, and it is the first one. And this is a prepare and measure base. So here, what our conventional characters are Alice and Bob. Alice and Bob are trying to establish a key between them. So Alice actually chooses between 4 possible basis choices. So essentially the rectilinear and diagonal. So 0, 45, 135 and 90. These are the 4 possible choices for bit values. So she randomly encodes one of them on her photon. And then Bob also randomly chooses a basis to measure the photon in, and comes up with a certain answer. So this goes on. So random choice of basis on both ends, and they end up measuring and sending different types of bits. Then what they do is, over a classical channel, they share this basis choice information, only the basis choice, not the measurement result. So they share that, okay, this is the series of measurement basis choices I have done, and then Bob also shares the same thing. And then they actually discard all those runs in which the basis choice was different, because it's random, it can be different, and only keep the ones where it is the same. Okay, and so essentially this is the idea. Alice and Bob have a certain set of operations, and then together they share the basis choice and come up with a certain set of bits where the basis choice has been the same. And so this is the sifted key. So essentially, critical elements to be developed in QKD, well, the most important element, I would say, is the source itself, because you really need a true single photon source in order to make this work. Because if you don't have that, then you have these various types of attacks from the eavesdropper, which are on multi-photon based attacks and so on. So this, of course, makes it natural for us to be involved in QKD for a long time now, because we have been working on sources. And so then, of course, you need to have good simulation ideas and developed, as well as, of course, the QKD protocol itself, which is going to establish this key. And then you have certain classical post-processing steps which are required to get the final secure key. Why do we need entanglement? Entanglement is needed because beyond a point, we don't even want to trust the devices which have given us this QKD. And if we don't want to trust the device, because some malicious malicious device manufacturer could put in some bias, and that would lead to a security loophole. So we don't want to trust the devices. So if we want to go to device independent QKD, then entanglement is the only known route towards that. And also we know that certain attacks are not possible in entanglement-based QKD. So our experiments at RRI Bangalore on quantum communication, well, of course, we have done both prepare and measure-based QKD experiments as well as entanglement-based ones. So the prepare and measure ones are done using single photon sources and non-orthogonality of states. Around 4 years back, we did the first BB84 demonstration. More recently, we have done an interesting take on the B92 protocol, which is not quite exactly the same as the one proposed in 92. We have actually put in a lot of interesting novelties in terms of the choice of source, the choice of detection, how we get the non-orthogonal states, and also optimization strategies that we have used, which has made our implementation different from the ones which exist, and in fact, much more favorable in terms of key rates and quantum bit error rate, as we would see. So this is how the setups look in the lab, the Alice and Bob setups. And you can find more details about the experiment, of course, in this particular paper, if you're interested, because I won't be able to cover too much in this short talk. So here you have the photon source based on SVDC. And then this is the Alice part of the protocol. This is the Bob part. And here you can see that we have a key rate of around 50 kilobits per second and a quantum bit error rate of 4.79, which is less than 4.8. Now this 4.8 is a very important number because we have taken a lot of pain to ensure that this is less than 4.8, because 4.8 is what is called the information theoretic security threshold for B92. So if you want to do a protocol, demonstrate a protocol, it's not enough to just say that, okay, I have this key rate and Q bar. The Q bar has to be below this threshold. Only then it is useful to give you the ultimate secure key after classical post-processing. Because other than that, it is not even a good candidate. And so this involves a lot of information theoretic calculations as well as alignment and analysis, which gets you this sort of a number. And so to our knowledge till date, the best available B92 setup has reported a key rate which is lower than us, a QBER which is much higher, and a 0.4 meter transmission, whereas ours is 2 meters. So of course, at longer distance, we want to even go further. Of course, that is the idea of long distance. And of course, students being students, they have also done an image encryption using this key. And so you can see that Alice and Bob have the same image. That was the intention, because our key is actually almost error-free. It is much below that threshold and so on. If this had a lot of error, then we wouldn't be able to do this as well. And we might end up with a completely different picture rather than the one intended. So this is also very important. In entanglement-based QKD, we have, this is our entangled photon source schematic, which is using a Sagnac geometry. And these are our Alice and Bob setups, and this is the entangled photon source. We have established what is called the BBM92 protocol, which is an entanglement-based QKD protocol. And in fact, this is also very nice. Our concurrence for entanglement is 0.995, where the highest value would be 1. So this is actually very good. This is one of the highest that we know, because it makes our protocol also that secure. The quality of entanglement is very high. So this is the general this thing. And in the process of doing this, we actually came up with an interesting simulation toolkit as well. When we were doing all these experiments, we realized that, what would be the best strategy? What would be the best set of equipment to use? Can we do some simulation for that? And we realized that, the ones which are commercially available are not quite living up to our expectations. So we came up with it ourselves. We call it QKD Sim. And in fact, this paper, which has the experiment on this modified B92, also has details of this simulation. So there are simulation toolkits which exist in literature for QKD. But what we wanted is one where there is a quick and precise simulation of physical processes considering realistic experimental imperfections. So for instance, the source, the detector, the background noise, and applicability to all protocols. And so there is no one software or toolkit which does that. And we understand the reason why, because you see, all they do is essentially just simulate the protocol without worrying about the fact that an experiment is never ideal. And this is probably because it comes from people who are maybe more software engineer type people. But when we experimentally start doing this, we realize that, a beam splitter is not going to split it 50-50. So all this has to come in, and that is what is going to give rise to an expectation, which is expected to match once your experiment is done. And so this is what QKD Sim is. And with QKD becoming commercially viable, you just can't keep testing these techniques in the lab on a table, because then you can't keep buying these products, right? So QKD Sim actually helps here because it takes into account physical process models, realistic imperfection, and experimental non-idealities. And we have, of course, tested its performance with our own experiment in the prepare and measure category. And we have followed what is called the AGIFOL model. Skipping the details of the optimization strategies, here you can see how well our simulated results match our experiment. And so that is very nice, because now we can, with confidence, invest more in when we go to longer distance and more complications. We, of course, know exactly what to do, at least to a great extent. And so this is where it comes in handy. This is the comparison again. Moving on to long distance quantum communications. Of course, till now we have been talking about quantum key distribution and quantum communication and the need for it, and of course all the experiments that we have been doing at RRI. But then our focus, so all these experiments have been under the ambit of long distance. And so why do we want to do long distance? Of course, it's, if you want to do secure communication, you just don't want to do it between, two entities which are really sitting next to each other. So you want it to be between cities and between countries and so on. And so the problem happens with typical ground-based systems is what is called line of sight. So you need to be able to keep seeing each other in order to get this key distribution to work. And then the demonstrations at best can go up to maybe 300 kilometers. Then the horizon, for instance, also becomes a problem. Now you can go to fiber, for instance, but fiber, as you know, there is a loss of, a certain loss per kilometer. And so then what do we do in classical communication is we boost the signal by using what is called a repeater. But then now you can't have a repeater in the conventional sense in quantum because, of course, of no cloning theorem. So you have to come up with a whole new strategy for increasing the distance of quantum communication. And there are two known strategies which are being investigated worldwide. One of them is using repeaters and relays and quantum memories. And the other one is using satellites. And so the repeater, relay, and memories is something we are also investigating in our lab in a project under the DST Quest program, which I will skip for now. So I'll go on to the satellite application. So what about satellites? So what is going to happen is that here you have a ground station Here you have another one, and they could be very far from each other, okay? And so then the satellite is going to come to one of the ground stations, exchange a key, okay? Then go over to the next one, exchange another key, and then by some mathematical operations, actually the XOR, we are going to actually establish a key between the two ground stations. So the satellite here is acting as a trusted node. And in principle, then you can see that it is not going to be limited to a 300-kilometer distance. It could be very, very large. And so this is the idea of satellite-based quantum key distribution. The role of the satellite is to help in the long distance aspect of quantum key distribution. And there are different distances one can reach using different methodologies. With repeaters, you can go only up to this much. With satellites, you can go higher. So what we want to do finally is make this very, very long, combining the two. So here you have the satellite-based QKD, which is our project. And then, of course, once this is established, this ground station is then going to communicate with different user agencies, maybe through a fiber network. So that is okay, because you can have different networks connecting different nodes, and ultimately the entire country will have a quantum communication network. And then what we are looking at futuristically is what we call the global quantum communication network, or the quantum internet, where the whole world is connected through a quantum communication network involving different satellites and ground-based, fiber-based systems. So this is the general idea. This is a very important area of research globally, lots of work happening. And of course, the only satellite that exists, the quantum satellite that exists, is from China, which is the Michia satellite, which was launched around 3 years back. And there is no other quantum satellite right now, but there is a lot of effort, including our own, towards adding more satellites and increasing distances and so on. And so these are all the various efforts that are happening worldwide. Our own effort started in 2017 under the project called Quantum Experiments with Satellite Technology, or the QUEST project, which is a collaboration between RRI and the ISRO. And so this is the general idea. So essentially, we want to establish information theoretically secure quantum communication over large distances, perform QKD between two ground stations. So that is what we would like to do. But then also under the ambit of this project is a collaboration with Canada, where we want to establish a quantum key between an Indian ground station and a Canadian one, which would of course be thousands of kilometers. And if you're able to do that, that would be some sort of a distance record. And so this is what we are working on for the last 3 years. And all those experiments that you saw, both prepare and measure, as well as entanglement based, and the new developments that we have done, including the QKD SIM, are all under the ambit of this QUEST project. And now we are poised to actually do free space, atmospheric, across the atmosphere, outside the lab QKD. So this is what we are currently working on. So here you can see our portable ground stations, which are already there. And now we are, as we speak, we are actually doing a free space QKD across RRI. And so that is the general idea. And as an overview, I have one more slide. And so as I just mentioned, so this is the long distance QKD project that we're working on, which is satellite based. Other than that, we're also working on integrated photonics based QKD under an Indo-Italian project, which is going to be chip based QKD. Then we have a project on quantum teleportation. Again, something I don't want to get into the details. Under this, this will also involve the relays and the repeaters under this DST Quest program. And then recently we have a project under from MIT, which is on quantum random number generation. Again, a very important tool, not only in quantum communications, but of course has many applications. So with that, of course, I would like to finish my talk. So this is some pictures we took in a conference that was held, a physical conference that we could afford to have in January this year, with a few visitors also in this conference. And hopefully soon we will get back to the mode of physical conferences and physical visits. And it would be very nice to have members of this community also visit us when that happens. So thank you very much.
Thank you very much, Urvashi, for a nice and very informative talk. And time for some questions. Arindam, I see you want to ask a question. Please ask. Arindam, can you hear me? Hello. Urvashi, can you hear me?
I can hear you, yes, yes.
No, I see in the chat box, I see a message from Arindam that...
I think Arindam just appeared and disappeared.
Oh,
on
maybe
video.
some connection.
Can you hear me?
Yeah,
So
now we can hear you. Yes, please.
Okay, I think there's a problem with my classical communication device, but anyway.
yes.
So Urvashi, thanks for the talk. It's very nice. Okay, but I have a small problem here. The
Okay.
problem is, while this is great and getting this technology up and running is very important. What I didn't understand is where's the scientific challenge?
Oh yeah.
In terms of where's the new disruptive part of the technology, or what is exactly what we will be where a new physics student would like to do.
Sure. So you are only talking about the quantum key distribution part.
Anything about this whole talk.
Oh.
What would be this fundamental science challenge?
The whole talk, of course, started Arindam with lots of different things which were
No, I was there throughout. I was there throughout.
So,
even the PRL that you showed.
Oh, yeah. That one is an interferometer. So I didn't want to talk about it because it's 25 minutes. So let me just give you a 1-minute answer to that. So I can come back to QKD. Then the QKD, the scientific challenge, of course, is different from what is the whole talk. But too many animations is a problem. Now that we are having questions. So of course, if you think about it, so if you now, of course, when you talk about fundamental tests of quantum mechanics, so then there is nothing that is, so this is of course as physics as it gets. And of course, we are all physicists, as you know. And so if you want to come up with a correct, want to understand the superposition principle better, or quantum superposition or quantum entanglement for that matter, or even let's say, various other topics in quantum domain. These are all experiments that are done using single and entangled photons, and they are precision experiments. So they cannot be this is something which is as novel as you would get. In terms of the Hongo-Mandel experiment that I talked about, as you may have realized that we have shown that this can be done using classical pulses and phase control. So this theoretically also did not exist earlier. So we've done the theory and the experiment. And so Hongo-Mandel is something that only happens, 100% dip only happens in, you call it, say, a photon bunching, right? That is the second chapter of a quantum optics book. But we have shown that you can actually do it using classical pulses. So again, something which stems very much from fundamental physics. And now going on to this quantum state interferography, this one actually is a very interesting one. So what we have shown is that you can have a interferometer. We have shown it using displaced Sagnac, but a Mark-Zehnder interferometer will do. And what you, by actually certain operations, which I won't get into for the lack of time, but you can actually define certain operations which you can perform, whereby you know what is tomography, I hope. So essentially what you do is you project your state to different bases, and then you reconstruct that state, because you can't just measure a quantum state. So that is all you can do in conventional methods. But here what we've shown, that tomography actually scales as the dimension grows up. So it is a square actually. But here what we have shown, it's a linear scaling. So you have an interferometer, which has to be very precisely aligned. And then you have the quantum state come in, and by doing the interferogram measurement, you can infer the quantum state from its intensity and its phase and the azimuthal. So essentially just from that interference pattern, you can infer this quantum state. And this work that you see here, while we have demonstrated it for qubits, we have also shown how you can infer the entanglement of a bipartite state. So this bipartite entanglement, as you know, it requires 3 measurements for a pure state, pure bipartite state, and here we require 1. So this is something very useful, because if you want to use this for any application, then you will be actually doing a much better experiment, because you will have less measurements, so less error. And so in some sense, this stems very much from as old as it gets, that is interferometry. So you cannot do much older than that in terms of quantum resources, right? And then of course this higher dimensional thing. So this particular setup that we have established, we have actually used spontaneous parametric down conversion and changed it. And so that's something I don't want to get into, but that's something which involves changing how we look at down conversion and generating the higher dimensional states straight from the crystal, instead of actually doing something later. So this exact setup is something which we have devised, and of course all this that you see is theory as well as experiment towards that. And now we are working on quantum gates. which
So
I find students are very, very interested in. So
maybe
talking about a physics
I
student.
think,
So,
Urvashi, that's enough. I mean, there are going to be other
there are
people also
lots of,
asking the question.
you talked about beginning, so I went to the beginning, but yeah, but then I can get to it later. Yeah, sorry, I don't see the questions. So somebody's going to.
hello.
Yes.
In the interest of the time, I would urge that let us move on to the next
Sure.
talk.
Yes.
And thank Urvashi for a nice and informative talk on quantum communication. So the next speaker is Saikat Ghosh from IIT Kanpur, and he will talk about quantum synchronization. Saikat, please come in and share your screen.
Hello.
Hello.
Yeah, can you hear me?
Yes, I can hear you and I can see your screen as well. Please, go to the, this is full screen now. And is your cursor moving?
Yeah.
Yes,
Can you
I
see
can
my
see.
cursor?
Yes, I see your cursor moving. So that is good. Please go ahead. You have 30 minutes and I'll tell you at 25 minutes.
Okay. Thank you, Brijesh, and thanks the organizers for giving me this opportunity to speak in a condensed matter, like the biggest probably the condensed matter symposium. While I am kind of similar to Urvashi from the optics and atomic physics background. But also, like, we have some recent interesting results which I thought might be very relevant, and that's actually on quantum synchronization, or actually observing for the first time synchronization in the quantum domain. And that's what I'll be trying to communicate in this half an hour that I have. So synchronization, firstly, I think this is a very learned audience. So I think everyone has heard the word synchronization. It's a spectacular phenomena. Naturally, people see, for example, this picture that I had in the first slide, and also here are actually this phenomena of fireflies in the forest. Certain species of fireflies actually they synchronize, and then one sees this beautiful light patterns. People actually in engineering, it's a big field, particularly in power grids. Synchronization there sometimes can play adverse effects. The whole thing can come in sync. 50 or 60 hertz in windmills, actually they are used as a kind of effective tool to increase the overall power. In muscles, the heart beating turns out that is a spontaneous synchronization. Like there are many physical organs that are operating through synchronization. Even people are now saying that effectively the brain and our long-term memory are basically little oscillators that are synchronizing. So instead of talking about classical synchronization for a long time, I just want to show one little video, which is kind of also will form an classical equivalent of the talk, the outline of the talk that I'll be giving. And what we'll be looking at, let me see if I can play this video. Yeah, so what we are looking at are actually the synchronization of fireflies. So what you're seeing is a video, night is getting darker and you will see the fireflies. Yeah, the fireflies are just coming up. So just before I go in, you will actually start seeing this fireflies blinking. And this is actually video of an experiment where someone asks this question that, these fireflies start blinking and after a while they synchronize. They have a small feedback, like they observe each other and accordingly adjust their period. But what happens if we actually instead externally perturb and put a LED, a flashing LED, can we make the firefly synchronize to that? And that's the video. In fact, it's quite spectacular, this experimental result one can see. So these are the fireflies actually starting to blink. And this is the LED. This is one of the circuits of LED that's actually blinking. So yeah, this is the LED blinking. You can already see there's a firefly next to it that's synchronizing here. You can see the firefly actually, and now slowly the whole forest is lighting up, all kind of being guided by the single LED, and all of them are starting to adjust to the phase of that. So maybe I'll, one can go ahead and watch the video. I'll just stop here. So So this is kind of the outline of the talk. What I'll be talking about is exactly this phenomenon. That's why this video is kind of important, except that, you know, for my talk, these fireflies will be replaced by spin systems or atoms with spin 1. And the LED will also get to a very exotic or kind of nice look. So, so before going into that, let me just, since I'm talking of classical synchronization, let me kind of summarize what is a very well understood field of classical synchronization. And all of classical synchronization starts from what are called this limit cycle oscillators. These are like self-sustained nonlinear oscillators. There's a pumping, there's loss, and somehow it reaches to a you know, a limit cycle, which is a fixed amplitude but no definite phase. And that phase that is not definite in a limit cycle oscillator can actually be connected, you know, to couple to an external reference, the way we just now saw the video that, you know, each of those fireflies were actually limit cycle oscillators. The oscillation, the flashing is going on, but then there's an external reference, which is the LED, and it can couple to that. It can couple to each other, like normally what they do. You know, this can form a network. This can actually be a network, you know, globally spread network, like the satellite network synchronization. There can be just two of them coupling. The master slave is also an example of the one just now I talked, where single LED basically is coupling several of these fireflies. And of course, there might be a more global coupling. So this is kind of the classical synchronization. These are the various different scenarios people look at. And before going away from this, what I am talking of, this limit cycle synchronizing, you know, so what is a limit cycle oscillator? This is exactly what I kind of trying to define, that if we think of our sense of harmonic, like our oscillators in phase space, classical phase space, position and momentum. So basically an oscillator is a point here, which is a vector, which has an amplitude and a phase, and a limit cycle oscillator is basically effectively a nonlinear oscillator. There are nonlinear damping and gain terms. Effectively, it has reached an amplitude, but it's not a single point. It is this whole cycle. It can actually lie anywhere. So its effective phase is actually not specified. And the process of synchronization, the simplest of this, is basically that this unspecified phase, if one puts a little tiny little phase perturbation, that's a little blue arrow, one can actually lock this phase to a specific part. So the limit cycle, when it actually sees this perturbation, it actually locks to that phase, and that's the phase it picks up. This can be an external reference like the LEDs, or it can be my neighboring firefly, which is blinking. So that's the idea. And just so that, you know, this is a confusion people have early on when they start thinking of what is synchronization to an external forcing, because isn't that what happens for a forced oscillator, right? Like if I'm forcing an oscillator, by definition, the oscillator is always synchronized to the forcing, but that's not the scenario of what is classical synchronization. And you can see that through the phase perturbation. Like if you try to synchronize this forced oscillator to another oscillator. So this is basically a time trace of a forced oscillator. At this instance, one gives a perturbation, so it kind of gets shifted. But you see that after a while, that perturbation dies off and it settles down to the original forcing phase, right? Whereas this is a limit cycle oscillator. Otherwise, it looks exactly like a forced oscillator, except the mechanisms are internal, nonlinear dynamics. But then you give a phase perturbation, and it just forgets its earlier phase and just picks up that phase, and from there on, it actually goes oscillating like that. Okay, so this is a kind of just a point. So basically, the question is, you know, like we talked about this limit cycle oscillators, classical oscillators, a little phase perturbation, you know, it synchronizes. Can quantum objects like atoms or spins synchronize to external forcing and to each other like that? So this is a question which has been around for a long time. You know, the community has been asking about quantum synchronization for the last 30 years very actively. And the general approach has been this, that the classical synchronization, mostly people understand either through like Van der Pol kind of oscillators or Kuramoto models for large number of such synchronized oscillators. So similar, you know, a nonlinear Hamilton harmonic oscillators. So they are basically like nonlinear, you know, damping terms and so on. If one takes such an oscillator and quantize it. So this is a quantum version of that, and then looks at like very low excitation regime. Do you see something very spectacularly different than what you expect in classical synchronization? And can the system actually synchronize? So here again, like the way you look at it, you look at the phase space, the state of the oscillator in phase space. You look for the states which are limit cycle like states, and then the signature of synchronization is basically when you have a localized state. There's a definite phase, and that starts processing. So that has been the thing, but the experimentally, these are very hard systems of actually getting these oscillators to very low excitations or very close to ground states that people have done in the last 1 decade, but also to actually engineer this nonlinearities at that kind of low temperatures has been a big challenge, and not much progress experimentally at all in this direction. There has been kind of a parallel question people were asking, and particularly this paper in 2018, where they started asking that what if we look at quantum systems which have no corresponding classical analog like a spin system? Can there be concepts of synchronization in a spin system? And so to talk about synchronization, first, can there be concepts of limit cycles in a spin system? And remember, we are talking of spin systems, so there is no position or momentum, but they actually, these guys, Alexander Roulet and Bruder, they actually developed a technique which had been around for a long time, this visualizing the states and this spin coherent basis. I think earlier Shubhashish talked about this, like you can actually create this semi-Q functions, in the phase space of the spin states, and so you can look at states which are like limit cycles. And first in this paper, they actually proved the Nogo theorem. They actually showed from very simple symmetry argument that, for a qubit or a spin-off system, there cannot be a state which is symmetric. So the minimum dimensions you need for a quantum system to even have a limit cycle is 1, 3 dimensions, so spin 1. And so basically, like just consider a spin 1 system like these 3 states. For example, if you take the spin and prepare it in this middle state, that actually corresponds to a limit cycle. So if you look at the corresponding phase space distribution, you see that it's actually like symmetric about an axis, and so this is basically was their point, that you create a limit cycle by creating one of this population state, and then if you can actually perturb the system, so this is like turning on an external forcing, and the perturbed part of the state has this off diagonal terms. So these are basically just you're creating atomic coherence. In that case, this limit cycle state actually like localizes to a synchronized state, or rather localizes and picks up a definite phase. So that's the kind of the experiment that we went ahead and tried to do in our system. So just to kind of outline what I'll be talking about, so just setting it up into like these parts, and I'll be constantly using the analogy of that fireflies. So basically the 4 parts of the experiment. First is to get this firefly. So we do this with rubidium atoms, so to trap and pull these atoms, so to get them in one place, then actually get a limit cycle state. So that's like getting the fireflies to blink, then turn on this LEDs. So that's kind of a part which is a little complex, creating this atomic memories or storing light in the system. And then finally also some reservoir engineering, which all these 4 steps done properly is when one can actually see coherence. So let me just go step by step. So the first part is pretty standard. We actually use laser cooling and trapping. This is a almost a 30-year-old field, but needs to be done very precisely. And when done precisely, this is a picture of the experimental setup. It's a rather ghetto, small setup. There's a little glass cell. Everything is homemade. Though it looks ghetto, but there are like some 40 remote controls that goes in controlling every aspect of the experiment. And so we start with a cloud of atoms. So the picture you're seeing is just a kind of a mobile camera picture of about 1 million atoms spread out over centimeters, and it's a cigar-shaped magnetoptic trap. So there's a large optical depth in one direction. So that's first like getting the atoms. Then preparing a limit cycle state, so you need to get these atoms to blink or the fireflies to blink. So that we do this is a little technical in the atomic physics community, but rather this is the hardest part of the thing. In quantum technologies, this is called known as state preparation. So you actually need to very precisely control the magnetic fields. So just to give you an example, this 87 rubidium that we use have two ground state manifolds, corresponding to the hyperfine states. F equals 2 is where we trap the atoms, and then in the state preparation, we actually bring the atoms, all of them, we turn off the magnetic fields. You need to be very careful to ring down all the magnetic fields to 0, turn on a little magnetic field as a quantization axis, then bring the atoms down to F equals 1, and then spin polarize them all to this middle state. So that's, if done properly, we prepare this whole cloud in the state, and that corresponds to the Husimi-Q distribution, which is basically all individually, each of these atoms, all of them are in the cycle state. So this is basically, I'm saying this very shortly, but the experiment is done over a period of total like 13 milliseconds. We trap the atoms for 10 milliseconds. These are like mod coils. Maybe I'll just skip this part. So there's all this timings. There's this part I described as a state preparation. Now comes the interesting part, that now you have gotten the fireflies, you have gotten them to blink. Now you have to make your LED little circuit and turn that on. That is the external forcing to which you want to synchronize. And that's basically a technique which we call the stopping and storing of light, or technically what's called the quantum memory of light. And that is, very simply speaking, a method of creating atomic superposition. So Urvashi was talking about quantum superpositions earlier. So creating off-diagonal terms in the density matrix, which are stable, so superposed states. So that's what I'll be talking about. So just a very quick, I don't know how long I have, like 2 minutes introduction to atomic physics, and what we do in the lab. So superposed states actually are made even in a tube light, or whenever light interacts with atoms. And if you just think of our quantum 1 course, so if you take 2-level atoms, send a laser, look at the detector, scan through the resonance, we basically have just 2 couple levels, the Rabi problem. We solve it by actually taking a superposed state. And when we solve it, we find that there are Rabi oscillations, basically, except these 2 upper and lower points, every point here at these times are basically when the atom is in a superposed state. But actually life is more complex than that. There are decays of the excited state. And so eventually we don't really see these oscillations experimentally, but we see kind of this absorption profile with a line width which bears the signature that the excited state is bad, and it decays out. So there's a way one actually can add a second field and a ground state manifold. And in this case, you basically have the excited state 3 connecting to 1 and 2 in a very specific way. So naturally in the system, a dark state forms, which is actually orthogonal to this bright state. And when you do that, when the atoms actually get trapped into that dark state, literally your excited state goes away. There's no spontaneously scattered photon. So you kind of have gone into a decoherence-free subspace. There's no noise, actually. And this has been the main tool in atomic physics to create stable superposed states. So this method is called electron magnetically induced transparency, because literally this 2-level absorption that you see when you turn on a second field, with the right thing, you actually see that the atoms get strapped to the dark state. So right where you are seeing the maximum absorption, you see a transparency, all the light goes through because the atoms are trapped in a superposed state. So that's the main key thing. And this is the coherence actually, so in atomic physics, this terminology, the diagonal terms we call population, the off-diagonal terms we call coherence. So this is the superposition that's actually created a dark state, which is the superposition rho 1, 2. And this is the same superposition that earlier this Bruder and Roulet, they were proposing as kind of turning on this external forcing, this coupling to actually synchronize. So that's kind of what we do here. I just wanted to mention quickly that this atomic coherence of superposition is something we have been working for a while in things like probing, quantifying, freezing, or Zeno-like, stopping from decoherence, and finally, synchronizing. So over a period of like 4 years, we have been looking at various aspects of this atomic coherence, and I'll be talking about only this one, this last one. So, how the superposition looks like, why I call it a quantum memory. So let me just describe how a typical experiment in the lab looks like. So this is a probe field which is going through, hello?
we can hear you. Yes, we can hear
Okay,
you.
yeah. Okay, I just thought I just dropped out. Yeah, so
No,
this,
no, no.
just imagine that there's a pulse of light which is going and falling in your detector. This is how the pulse of light looks like. Now you trap the atoms in the middle. So basically what you will see actually that now the pulse is getting absorbed. That's a red beam. So because, you know, this is actually like resonant and that's what is happening. But now if you actually turn on a beam which is perpendicular to this, you know, this is the control field. Again, you see that the red beam was when only omega p it was absorbed. Now you turn on the control field, you see that again the pulse comes out. Though this pulse looks a little different than the earlier pulse, you know, it's a little broader, it has shape. And this pulse actually is very interesting because this is a pulse which is coming out, is actually interacting with the atoms. And this is actually the right way of thinking of it, is that it's actually a polariton. So half of it is in the atoms, half of it is in the light. And the way is that, you know, experimentally when we turn off the beam some point, you know, you see that we have not kept it on with this control field for a long time, but turned it off. Later, when we turn it on, we see that this pulse that got absorbed actually comes back out. And during this time, it's actually stored as a superposition of atomic states. So this polariton, which in the community is called the dark state polariton, has a part which is purely optical or photons and a part which is purely atomic coherence, you know. And the best part is that this mixing terms you can actually control by controlling the field intensities, you know. So these are knobs in your lab that you can do. We actually, this has also been around for 15 years or so, this stopping and storing light. What we did, we extended this and we actually used the spin one system, which has 3 ground states. So you see there's a superposition because of this control and the probe, but there will also be a polariton forming here. And if you look closely, in fact, experimentally, we find that this model matches very well, that now there are 2 polaritons. One is rho 1, 2, but the other is rho 2, 3, with the corresponding probe fields. And what we see, or what you are going to see, is actually a superposition of these two. So that when you retrieve the light pulse, you should actually see these 2 atomic coherences are interfering exactly like a beam splitter. So you can actually map it exactly to a beam splitter problem. So these are experiments. So, you know, this is actually, you are seeing a series of pulses coming in, getting stored, you know, so we shut off the control pulse there, the atom, so we change the coefficient. So during this time, actually, these are atomic states, you know, they're coherently stored, they're not scattered off like a tube light. And when the proof is when we turn back on, at different times it comes out, and this decay is the Doppler decoherence. You know, we can talk about that more. But the question is it really working for 2 coherences? You can actually test it very nicely. You can put a magnetic field, which actually creates different opposite phases for these 2 states. They relatively shift. And then as you start retrieving the light pulse at different times, you see oscillations, actually. So these oscillations are typical signatures that as it's stored for longer, there's a phase which is it's picking up, which is basically delta, you know, mu bz 2h bar times tau, the amount it's stored, and that's what is picking it up and down. So you can actually see exactly like an interferometer oscillation. So this is an experimental plot where every point is actually one of those experiments performed and retrieved at the same time. But here in this direction, we change the magnetic field. And in this direction, we change the relative phase between these 2 control fields. It turns out that when we change the relative phase between the 2 control fields, you also change the phase in the Hamiltonian. You know, that actually plays an important role. How long do I have?
Well, you have about 8 minutes in total.
Oh, that's great. Yeah. Okay. So, so basically, you know, just coming back to their scheme. So this spin 1 atom I'm talking of. So this effectively, you know, in atomic physics, it's quite common to right away see that this and this effectively forms a 2-photon coupling, and this forms a 2-photon coupling. So this actually couples the spin states, you know, so these are kind of the external driving field. The last part is kind of a very interesting thing, which I skipped earlier, that what they were saying is that, you know, if you want to synchronize these atoms or local, like, the question is whether the state is really getting localized. It's not enough to have this coherent couplings, which are the LEDs, but somehow you need to also engineer the environment or decoherence. And that is basically, you see that there is this, you need to actually engineer 2 decays. One is this gamma G from the upper to this state, and gamma D, both are decaying to the middle state. This actually stabilizes the limit cycle, it turns out. And this is normally, naturally, you don't have it in spin 1. So you actually need to make them artificially. So we do that by using like two further, like, counter propagating beams, which are not phase matched, so that they don't create any coherence, they just create like decoherence, So we can talk about this. One needs to be careful about the fields and so on. So this is finally the experimental setup. There's a control field, there's a recovery field, but there are this D1 and D2, which are the decoherences. All are going perpendicular to the probe field, which is getting stored and recovered. So this is the whole experimental setup, like the timing sequence. I'll skip that. But a very important part after all this is also actually to have a, we basically simulate this experiment and do this through this Maxwell block, which we have been developing through this earlier work also. So it actually simulates the system very well, unlike many condensed matter systems. So these are experiments, these are simulations, so we have very one-to-one correspondence. But the advantage of the Maxwell block is then we have a direct access to the state. And so from the fitting of the simulations to the experiment, we can actually reconstruct the state. So this is experiment, this is simulate, this is the reconstructed tomographic states. And you see that this is what we start with. We start with the limit cycle state, which is this first dotted line. But then we actually, right when we actually turn on this control fields, the state gets localized. It remains localized during this time 3, but in 4, when we actually retrieve back, it goes back to a limit cycle. So you actually see the localization as the synchronization physics. In fact, it's even more beautiful, like experimentally, when we actually put a magnetic field, you see that the state gets localized, but as it's stored in this region 2, 3, 4, you see that the state is precessing actually. This is exactly what one expects from synchronization, but actually that's not quite the whole story. It turns out that, as I was saying, these two control phases are very important. They play, like in the Hamiltonian, a very important role. So these two parts of the Hamiltonian, if the two controls are out of phase at pi, it turns out even in this kind of a scenario, there is no synchronization.
You have
so
5 minutes now. You have 5 minutes.
Yeah. So basically, you see, this is the earlier interferometer diagram, interference patterns I was showing. So region A is where this phase difference is 0. And there you have a synchronized state, the reconstructed state or the tomographic state. And region B, where the phase is pi, you see that the state is still not synchronized, But that is the most interesting part, that now we actually, now the decay starts playing a role. We actually make these two decays anisotropic such that their ratios are 11. And that's this plot. You see that the fringes have changed. This minima has gone up, and if we actually plot in C and D, you see both for region 0 and pi, the states are localized. In fact, this is just very technical, but one can construct a synchronization function from these fringes, so one can actually reconstruct the synchronization function. And you can actually see this is experimentally constructed, and this is the theoretical one. In this region, there is no synchronization. The synchronization is 0 in when the phases are pi. But when you put decays, asymmetric decays, it's quite surprising that decay actually induces synchronization. You actually see that the function is non-zero for the entire range. There has been, this general question that what is so special about quantum synchronization? Is it different than classical synchronization? And even with harmonic or nonlinear oscillators, people actually have predicted for a long time that for quantum systems, firstly, energies are exchanged in packets, and also there is interference, for the systems. So actually, interference can block synchronization, and that's exactly kind of what we see. So in this region, you see that actually what happens is these two controls actually creates two coherences which exactly cancels each other. And in the recovery and in the synchronization function, we see 0. But as we start increasing decay, it's very counterintuitive. We find that actually, you see that here the decay, the 2 anisotropy is 11. We are actually, the x-axis is increasing. One of the decay is gamma G, and you see that synchronization comes back, and it's a pretty large, Again, so this is something very counterintuitive, because normally synchronization, phase synchronization, we expect that phasing is always counter to dephasing or decoherence. But here, this is a case where decoherence actually breaks the condition of perfect destructive interference, and as a result, synchronization emerges. So there is another very technical thing. This is kind of something that the synchronization community wants to see. There's something that, if you actually now start increasing the driving strength, At some point, of course, it becomes a driven oscillator that's like, way outside the synchronization regime. But as you start increasing the driving strength, initially what happens, even frequencies which are outside the resonant condition actually starts getting synchronized. So you start seeing a tongue-like structure. This is there in classical synchronization. This is called Arnold's tongue. And that's exactly we see in a very spectacular way. So this is actually done at, the experiment is done with the two controls out of phase at pi. So you see this fringes as a function of magnetic field. This x-axis is magnetic field. Here you see destructive interference. As we increase the anisotropy, from 1 to 11, you see that this whole thing collapses to Arnold's tongue. And for equal decay rates, there was no synchronization at all in the synchronization measure. Here, the synchronization measure emerges. So with that, I think I'll just summarize that this is the first ever experimental observation of synchronization in any kind of system. And there's this paper just came out a couple of months back, and there's a nice synopsis they have covered in the physics journal of APS, where they actually talk about the system in simple words. And I just 2 slides or 1 slide effectively, that this is not the only kind of superposition that we work on. In fact, very similar synchronization physics and physics of coupled superposed systems we are working on with graphene resonators coupled to some other kinds of the silicon nitride resonators. And these are still now classical system, room temperature system, but we see, for example, squeezing, which we use to measure displacements down to 3.8 femtometers integrated over a second. But also we have seen that, these are very interesting systems where we have seen this generation of this phononic frequency foam. And now, over this lockdown lab period, we are starting to realize that basically there's very similar synchronization regimes in these systems also, but classical synchronization. So kind of a longish time goal over next 3 years or so is really, we have the spin-1 systems which we synchronize to classical forcing, whether this classical forcings can actually be replaced by this nanomechanical oscillators, so that we have a coupled system which can give us a liberty to kind of study, for example, graphene properties from atoms or atomic properties from graphene, besides the fact that we are also very interested in just pure classical applications like accelerometers and and so on. So with that, all the work are done by the students. What I talked about is Arif's 1/3 of his thesis work. Arif, Pratik, Shukrodeep, they have been working. There are some students about to join. Rajan worked on the graphene work. He has now moved to Weissman, and now Arnold and Atish have picked up. Chitresh is an undergraduate who almost stayed with us like a PhD student. Now he has just moved to Yale, to Jack Harris group, and it's doing fine. So with that, of course, a big thank to Sai, who has been a collaborator and a very big enthusiast for doing these experiments. Shaurin, who also proposed to do this experiment from ICER. Shagur, learning nonlinear dynamics from him. Harsha and Anand, talking to them all the time, and I want to thank you. So with that, I would like to have any questions, and thanks a lot for your attention.
Thank you very much, Ghosh, for very nice and very nice talk. I mean, very nice experiments, very nice ideas. So if there are any questions, people can ask now.
All right, can I?
Yeah, hi.
Yes, Arindam, please go on.
Okay. No, Shaghat, very nice. I read the paper. Congratulations. It's a very nice paper. I'm not from the field, so you have to understand the naivety of my curiosity here. So the question is, the pumps is, I'm trying to understand what's the next stage of this project. Is it, can one, demonstrate a real quantum repeater from this? Is
quantum what?
A repeater. Say, for example, can one go to that situation? Is it what would you think the the primary
Yeah,
challenge?
so let me make few comments. So one is that like my obvious next step, which we have been intrigued even earlier, is you see that like let's just go to this Arnold term. So this is basically actually the experimental data, and this is theory. And you see, I'll just make this comment that no matter how well we had those experimental and theory matching, but here you see that the experimental tongue is much narrower than the theoretical tongue. Which is basically saying, so let me just make the question simpler. The question is, really, is it that every atom is getting synchronized to the drive and there are a million of them getting synchronized, or this is actually going into a collective state? So it is known kind of in the community that whenever you have super radiant Dicke-like states, there is a spectral narrowing. The question is really, is that what we are seeing? And what kind of collective states the system goes into? Like, like we have been very excited about this. Unfortunately, the experiment stopped, but like these are kind of like what people talked about earlier, like phasonium kind of, some sort of a very interesting phase coherent states. The atoms are still widely separated, but like their de Broglie wavelengths are not overlapped, but there's a phase relationship between them. So this is one part. Yeah.
Sorry. So when you say it goes to a collective state, I'm sure the lifetime of that collective state is going to be of importance. What is the
lifetime of the collective state would basically, would be the lifetime of this coherences that we have, which are basically the Doppler lifetime. Okay. So we are kind of doing it in a very bad geometry where we have a lifetime. The total memory time of these photons are basically 1 microsecond.
Okay. Okay.
But of course, that is another like very important point that people have shown that if we go to a collinear geometry, which presently we don't know how to do the experiment in a collinear geometry because of quantization access. But if you are in a collinear geometry, you can have memory time of this the spin memories to be up to an order of 1 second. So now, as far as the application is concerned, the way I think of are like now you have this multi-nodes over a network. Like these nodes, the network might be actually physically separated over few labs, or maybe actually this network of atoms which are there in the cloud. So now the question is basically, can you initialize them all by sending this classical field over the network, and all of them synchronized to the classical field, and as a result, the quantum states are all synchronized and they are all the same. So that would be, I don't know whether that would be making a repeater, because this is already like the quantum memory is there, but this is more like synchronizing the memories.
Yeah, I understand. I mean, I think your direction is, I mean, whether one can put it in a small package probably would be interesting as well. So.
Just a small query on, I mean, that I have for Saikat. See, I mean, I couldn't completely grasp everything that you have been saying and doing, but
I said a lot of things here.
But it is still like individual spin one that somehow whose dynamics coupled to bath and the source. Is that what you are studying?
Yeah, it's a single spin phenomenon.
Yeah, so but what I'm saying is the inter-spin interaction or their collectivity is not going to play any role, or is
so
it?
So that is the $1 million. That's exactly what I was trying to say. That like here we have a cold gas of atoms, not ultra cold. So the atoms are widely separated. So this is an ideal gas for all practical purposes.
So you're saying it's effectively ideal like or very far separated atoms.
Yeah, so the simulations are actually all single spin simulations, so they're basically saying that the matching is basically saying that what you see for one atom, you see 1,000,000 times that. So it does that. But also these atoms are supposed to have because they're all coupled to the same radiation mode. So these are actually supposed to go into super radiant states.
Yeah, they have to form Dicke-like states.
Yeah. So the question is, what are the signatures of that? So now you see that they are also each of them are phase coherent. Like each of the spin one states internally have the same phase. So what is the Dicke state corresponding to that spin one system? That's really the question.
Just one last comment and then we move on. Urvashi Sinha has something to say. Would you like to say, Urvashi, or shall I read it?
No, I was just saying that, if you have to have a traditional quantum repeater, that would actually involve quantum entanglement. So essentially you would have a quantum relay, which would swap the entanglement, and then you would have these memories, which would form the nodes. And that is the traditional sense of a quantum repeater. But then what we would have with Shoikot's thing would be, as I just mentioned, it would be some sort of a collective synchronization.
Yeah.
Yeah.
But just exactly what Urvashi is saying. So I just want to say that this whole field that I tried to describe very quickly, this field of sea-level atoms, this Lukin. So there's a very famous paper called DLCZ in the community, Duan, Lukin, Siraf, and Zoller. There's a 2001 paper where actually exactly this is the scheme. They actually talk about dark state polaritons and creating quantum repeaters, so that there the repeaters are basically like you can actually use exactly the systems to create entangled photons. There is a four-way mixing, or you can
Maybe
create
in the
photon entanglement.
sorry for
and
interruption,
then you can entanglement over the whole network.
but I think in the interest of time we should move on.
Yeah.
Otherwise, yeah. But it was very interesting talk and good discussion.
Thank you.
So the next speaker is Ahana Ghosal from HRI, and I would like, please share your screen, and you have 15 minutes, and I'll remind you at 10 minutes.
Yes. Can you hear me?
Yes, I can hear you, and I can see your slides and your cursor. Just move around your cursor and see. Yes, it is moving. So please go ahead.
Good evening, everyone. Thank you for giving me this opportunity to present my work here. Today I will discuss the paper Population Inversion and Entanglement in Single and Double Glassy James Cummings Model. This work is done with Sritama Das, Professor Aditi Shende, and Professor Ujjwal Sen. I will start with a model atom-photon system, James Cummings model. This is a single-mode quantized field interacting with single two-level atom, where nu is the frequency of the photon field and h cut omega is the energy difference between the two levels of the atom. G is the atom cavity coupling constant. Now, the two important phenomena of single James Cummings model are population inversion and atom-photon entanglement. This is the plot of population inversion with respect to time, and we can see that for a very short time there is periodic collapse and revivals in population inversion, and if we increase time, then the number of revivals increases, and for further increase of time we can again go to the shorter time situation and can get collapse and revivals. This work is done previously, and these are some references. In the right hand side figure, we have plotted the von Neumann entropy of entanglement with respect to time, and we can see that entanglement oscillates from 0 to 1, and then the system drifts far away from the maximally entangled situation and then again goes closer to 1. And this behavior repeats periodically, and for longer times the system goes to the maximally entangled situation. And now I will briefly discuss what is Quench disorder and Glassy James Cummings model. Professor Ujjwal Sen has already discussed about impurities and Quench disorder, so this is a repetition. And what is the sources of disorder? Disorder can be everywhere, and impurities can arise from missing particles in an array and fluctuations in the system parameters. Fabrication of perfect cavity with atom in it is challenging, so there are possibilities of fluctuations in tuning the components of the setup. Why disorder is important? Because they are there, and disorder can also be engineered. Sometimes, not always, disordered systems have advantages over ideal systems. In our work, we have considered fluctuations in system parameter, and the fluctuation can be of many types, and we have considered Quench disorder. Now, what is Quench disorder? If then it is called Quench disorder. If Quench disorder is present in a system, then we have to find the value of a physical quantity for a given realization of disorder and then average over all possible realizations. Say we have taken n number of realizations, and n should be large enough so that we can reach to a certain precision. If Quench disorder is present in a system, the system can be termed as a glassy system, So we have called our Jaynes-Cummings model as a Glassy Jaynes-Cummings model. This is the interaction Hamiltonian of Glassy Jaynes-Cummings model, and we have introduced a Quench disorder random variable delta with the atom cavity coupling constant G. If there is any fluctuation in the position of atom, then we can get a fluctuating G. So this is justifiable to have the disordered parameter with G. And this random variable is chosen from the disorder parameter
Hello. Hello. Your slides seem to be frozen, at least on my screen. Can others hear me?
No, we can hear you, so we
Yeah,
can't hear
so
her.
yeah, so Ahana's yeah, we are not able to hear you, and your slide is also frozen. Maybe some network problem at her end.
I think she got disconnected.
Okay. Let us give her one more chance. Ahana, can you, well, she's not here in the list.
Should I call her?
Sudeep, can you please call her?
Okay, I'm calling.
Ahana, yeah, I don't see her name in the participant list. So
She got disconnected.
maybe we wait for a few minutes, and
Yeah.
yeah, these are unexpected problems of this online seminars.
Sir,
Yeah.
Yes, you are back, Ahana.
yes, my internet connection is so unstable. Sorry for the inconvenience.
No problem. But if you are in a position to come back, then please come back immediately.
Yes.
Yeah, we are waiting to hear you.
Okay.
Yes, we can see your slides and we can hear you now.
Okay. From here, I can start.
Yeah, wherever you, this is your choice. Just start.
Okay. So, thank you. Oh, now I will discuss what is the effect of population inversion and what is the effect of disorder on population inversion and entanglement. This is the first one we have chosen, the Gaussian Quench disorder, and this is the probability distribution function. Mean is 0 and standard deviation is S here. In the right hand side figure, we can see that population inversion, in the population inversion, there is a strong suppression of the amplitude of revivals, and this suppression is exponential, and for a very small value of S, for S equals to 0.001 here, and we can get a very strong suppression in presence of Gaussian Quench disorder. And for entanglement, oscillation remains, but for longer times, we can see that population inversion goes to 0, but entanglement goes to the maximally entangled situation. The second one is the uniform quench disorder, and this is the population distribution function. And here we have chosen S equals to 0.1. In the population inversion case, we can see there is also a strong suppression, but this suppression is not as strong as the Gaussian Quench disorder case, and this goes with 1 by S. And the entanglement with time is almost similar to the Gaussian Quench disorder case. The next is discrete quench disorder, and P of delta is the probability distribution function. This is from the both the figures, we can see that there is a suppression of amplitudes of revival and entanglement, but the suppression is not so strong as Gaussian and uniform quench disorder case. So we can say that discrete disorder is more robust to these phenomena of the system compared to the other disorders. The last one is Cauchy-Lorentz disorder, and this is the probability distribution function given by P of delta. This probability distribution function is quite different from the other three, because mean doesn't exist here, and what we have to done this here, we have to take the median based averaging. And if we compare these two figures, that is, one is population inversion and the one is the entanglement, with Gaussian Quench disorder case, and we can see that the in two cases the behaviors are qualitatively same almost. So these were the four Quench disorder case, and now I am moving to the double Jaynes-Cummings model and entanglement sudden death. This is the double Jaynes-Cummings model. Atom A, hello sir.
Yes, we can hear you.
Okay. Atom A is interacting with cavity A, atom B is interacting with cavity B. Atom A and atom B are non-interacting, and cavity A and cavity B are isolated from each other. Now, H is the Hamiltonian for double Jaynes-Cummings model, and Ga and Gb are the coupling constants, and phi atom is the initial atomic state we have taken. This is an important phenomena, entanglement sudden death. Professor Urvashi Sinha has already mentioned this phenomena, and we can see here we have investigated the concurrence of atom-atom entanglement, and for single Jaynes-Cummings model.
You have 5 minutes, just to remind you.
Yes. In the previous case for for single Jaynes-Cummings model, we investigated atom-photon entanglement, and for this case we have investigated atom-atom entanglement, and we can see that entanglement abruptly goes to zero at a point, and at this point entanglement have a non-continuous derivative and remains zero for a finite interval of time. This abrupt vanishing of entanglement is called entanglement sudden death, and this work was done previously, and these are some references. Now I will discuss what is the response of entanglement sudden death to disorder cases. This is the Glassy double Jaynes-Cummings model Hamiltonian, where delta A and delta B are the disorder parameters.
Just one small query. I mean, you don't have any interaction between the two Jaynes-Cummings models?
No. Yes, I have no interaction between two Jaynes-Cummings models.
Okay.
So delta A and delta B are the disordered parameters, and this is the atom-atom concurrence, and this is the analytical result. So this is the response of atom-atom concurrence with in presence of Gaussian Quench disorder in the left-hand side, and in the right-hand side we have plotted atomic parameter and the disordered parameter, which are sigma A and sigma B, that are the standard deviation of delta A and delta B. And from this figure, we can say that disorder can wipe out entanglement sudden death. And if we increase the strength of the disorder, the entanglement sudden death wipe out very fast. And from this figure, we can conclude that high initial entanglement requires smaller disorder strengths, and low initial entanglement requires larger disorder strengths for wiping out the entanglement sudden death. This is the result for uniform quench disorder, and we can see that we can also wipe out the entanglement sudden death by using this disorder, but this is not as good as the Gaussian case, and the region bounded by atomic parameter and the disordered parameter where we can get the entanglement sudden death is quite large here. This is for discrete quench disorder, and as we see previously that it is more robust to this phenomenon, and there is a very small region in the atomic and disordered parameter space where we can wipe out the entanglement sudden death. This is for Cauchy-Lorentz disorder, and this is the
Hello, we can't hear you again, Ahana. Ahana, can you hear us? Can you hear me? No. Yes, she's again. Uh,
Sir,
yes, बोलिए.
again.
Yeah, कोई बात नहीं. Just yeah, you have just.
Okay, then I am going to the conclusion and
Maybe you can conclude in some
yes,
sort of
yes.
summarize your talk. If the network is a problem, at least
Yes,
you
yes.
can. Yeah, please go
Yes, yes,
ahead.
I am going to the conclusion. Yes. So the main result was the results are qualitatively similar for different disorder distributions, but there are major quantitative differences. So here I conclude that we considered response to quench disorder in interaction parameters of single and double Jaynes-Cummings models, and disorder may remove phenomena of collapse and revival in population inversion of time evolved state of single Jaynes-Cummings model. And even after oscillations in population inversion have died out, atom-photon entanglement continues to oscillate appreciably. And for double Jaynes-Cummings model, entanglement sudden death can be wiped out by disorder in double Jaynes-Cummings model, and different disorder distributions can induce significantly different behaviors, at least quantitatively. So that's all. And thank you.
Okay. Thank you very much, Ahana, for your presentation. A few questions, if there are any. Audience, you can ask her some questions if you want. Okay, I have just one small query. So your double Jaynes-Cummings are two independent JAC cavities, but where is the entanglement in the initial state, I suppose? I missed that point.
Yes, yes. The initial entangled state is entangled in
Uh-huh.
atoms, but this entanglement is created by some other mechanism independent
Hmm.
of the Hamiltonian.
Understand. So the state is prepared such,
Ha,
but
yes,
then the
yes,
eventual evolution is happening by two independent JC models.
yes, 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 yes.
Okay, fine. Okay, I think with this we sort of thank you for your nice talk and move on to the next talk.
Thank you, sir.
The next speaker is Srijan Ghosh from HRI, and Srijan will talk about enhancement in the performance of a quantum battery by ordered and disordered interactions. Srijan, please share your screen.
Yes, sir.
And you have 15 minutes, and I'll remind you at 10 minutes.
Yeah, sure.
Go ahead.
So, can you see my screen?
Yes, I can see your screen. Your voice is a bit feeble though. Can you speak again? Just see if it is audible.
Yeah. Hello.
Yes,
Yeah.
now it's better, and I can see your cursor. Where is your cursor? Let us see.
Yeah.
Yeah, it is working fine. So please go ahead.
Okay. Thank you. So, first of all, thanks to the organizers for giving me the chance to present my work. This is the outline of my talk. So, just for completeness, I will discuss what is classical and quantum battery, then various models of it, then the spin chain that can be used as quantum battery, then ordered system. I will define what is it later. Then the effect of temperature to our system, and the effect of impurities, and finally I will conclude. So let us start with this question. Does quantum mechanics help to enhance the performance of quantum battery than its classical counterpart? And obviously the answer is yes. And with this motivation, we can proceed that what is classical battery? A classical battery is a device consisting of one or more electrochemical cells with external connections for powering electrical devices. Basically, it converts chemical energy directly to electrical energy. And what is quantum battery? These two guys in their first paper of quantum battery defined it like a d-dimensional quantum systems with non-degenerate energy levels from which what can be reversibly extracted and on which energy can be reversibly deposited by means of cyclic unitary operations. So suppose this is a spin-off particle, B is the external magnetic field. We will say that the battery is completely charged or fully charged if the system is in plus E state, and if it is in minus E state, we will say that the battery is empty. So now the various models of quantum battery, these n copies of d-dimensional unit cell, the array of quantum battery. So the local driving field couples each individual ground states to its respective excited one. This strategy is a local charging procedure, and this is a global charging procedure, where this global driving field couples to the collective ground state to the collective excited states. And secondly, this decay model or cavity assisted quantum battery, where an array of two-level systems coupled with a quantized single mode electromagnetic field. Why I choose these two? There are many other models, but I choose these two because in the main paper I have taken these pictures from this review, but in the main paper they have shown by explicit calculation that by defining a quantity like quantum advantage, they show that quantum battery, rather quantum mechanics, really helps than its classical counterpart. So now spin channels quantum battery. So this is the first paper. As far as I know, these guys show that a spin chain can be treated as a quantum battery. So what they have done, they have a collection of isolated system, and they converted into a many body quantum system with intrinsic interaction. Now we have two parts. One is independent subsystems charged by entangling field. So these are independent subsystems, no interaction between them, and this is the entangling field. And another one is spin chain with intrinsic interactions charged by local charging field. We choose the right one. Yeah. So this is a schematic diagram of our scenario, where these are the qubits, the spin of particles. These are the local magnetic fields. This is the interaction between the qubits, and as we are discussing about a battery, we need to charge it, and these are the Hamiltonian, or rather the charging field. So in our paper, we consider the quantum XYZ model, where H is the strength of the magnetic field, J is the coupling strength, gamma is the anisotropy parameter, and delta J is the strength of ZZ interaction. Now, depending on the values of these parameters, we can have a families of Hamiltonian. For example, for delta equal to 0 and gamma equal to 0, we could have XX model. For delta not equal to 0, gamma equal to 0, we could have XXZ model, and so on. This J, this index defines the order case and disorder case. When this coupling strength depends on site, we will say this is a disordered system. If it is independent of sites, then we will call it an ordered system. So okay, so now one can just multiply some constant factor greater than 1 with this H part, and increase the efficiency of the quantum battery. So to make our analysis non-trivial, we just normalize this Hamiltonian and bound its spectrum between -1 to 1. And we are mainly interested in this interaction part. So the initial state of our quantum battery is the ground state, the thermal state of this Hamiltonian. So now, as I have stated earlier, that the charging field is on the x direction. This is a closed system, so the evolution should be unitary, and it is e to the power minus IHT. And we define this extractable work at time t, where rho t is the time evolved state via this unitary. And finally, we computed the maximum average power, as average power is power depends on time, so we have to optimize it over time. Then the ordered system. Now this J and deltas are independent of sites. So here we plotted the maximum average power with J for different values of anisotropy parameters, and it is very clear from the picture that as we keep on increasing J in the right side, we will get more and more Pmax. The Pmax value will increase. This J equal to 0 point is the no interaction part. So actually, we can conclude that interaction helps to increase the maximum power, maximum average power, and low values of anisotropy parameter is good to engineer the quantum battery. So now, why this is like this, we can try to argue this in such a way that suppose this figure is for delta equal to 0. So we have turned off the ZZ interaction. So now if J by H is greater than 1 and gamma is also greater than 0. So, and obviously this V charging is in X direction. So the system can be easily driven without demanding more energy. So we'll get less amount of power generation in this part. And if we consider J by H is less than 1, Then spins have this is the paramagnetic phase, and the spins have affinity towards the z direction. And so the as the charging field is on the x direction, so we need more energy to drive the system out of equilibrium. So we need high amount of power in this phase. Okay. Now we turn on the ZZ interaction for one and fixed its value to 1.0 and plotted the same, and see the same feature, but for j less than 0 gives higher power with non-zero value of ZZ interaction. In this plot, we have we wanted to see how Jmax behave with ancillary parameter now for different value, different system size. So now what is Jmax? Jmax is a value of J for which Pmax reaches its maximum value. And it's very obvious the spin models with low values of ancillary parameter perform better. So XX model is better than the Ising one. Now the effect of temperature. So as we all know that absolute zero temperature is almost impossible to obtain. So we consider the thermal equilibrium state of the system. That time rho equal to e to the power minus beta h by z, where z is the partition function, and we define a quantity like Pt max, where if Ptd max is greater than 0, then from this expression we can see that initial thermal state is beneficial than ground state, and if it is less than 0, then initial ground state is better than the thermal state. Now we have plotted a map plot with j beta and with this quantity. As expected, we can see that for beta equal to 0, there is no power generation, and that is infinite temperature. And as then if we keep on increasing the beta, our power will keep on increasing, and at beta tends to infinity, it will converges to the ground state value. But we can see that the increment or the increase of the power generation is not monotonic. Here is some non-monotonic bump, and so we can conclude that there exists parameter range in which quantum battery performs more efficiently at higher temperature than the initial state with low temperatures. So in this part we can say that temperature is non-zero. Still we are getting more beneficial behavior from our system than the ground state. Now this is the effect of impurities disordered system. Now the Professor Ujjwal Sen and Ahana has discussed a lot. I'm not going into it, just to say I'm going to the result. And we have considered here the Gaussian distribution. And in this plot, we have plotted the mean value of J with maximum power, keeping ZZ interaction equal to 0 for 0 unnecessary parameter and for different values of standard deviation. This is the gamma equal to 0 is a no disorder case. And we can see here that for a certain range in the parameter space, we can get a beneficial behavior from
You have 5 minutes, huh?
Yeah, thank you. Get a beneficial behavior like if sigma equal to 0 and this sigma equal to 1, so disorder actually helps to increase the power, and which is more prominent in the right figure, where we have plotted that delta mean equal to 1, and we have plotted against j. Here we can see that when standard deviation is 1, in the whole space, in the whole parameter space, we are getting beneficial behavior due to disorder. So disorder sometimes enhances the power generation over ordered case. In the literature, it's called disorder induced order. And finally, conclusion, interaction between the spins help to increase the amount of extractable power from quantum battery. And number 2, impurities present in the system can give higher power in quantum battery than the case without disorder. And thermal states are sometimes better than the ground state as an initial state. So this work has been done in collaboration with Titash, who is a postdoc now, and with Professor Ajit Shande. And that's it. Thank you.
Thank you very much. Thank you very much for your interesting talk on quantum batteries. Now, any questions, audience? Anyone? If anyone has a question, please ask. Well, if there are no questions, at least there is enough food for thought. People can reflect later and ask later. So thank you very much again for a nice talk. And with this, we come to the very end of the final session of this nice conference. Sri John, can you hear me?
Yes, sir. Yes.
Yeah. So thank you very much. And I think you can now stop sharing your screen.
Thank you.
And thanks very much. And thanks to the organizers for giving me this opportunity to sort of, listen to so many interesting talks and also chair these two sessions. With these words, I hand it over to Manoranjan, and yeah.
Okay, Brajesh sir, thank you very much for chairing two sessions and that too in like continuously. And
My
with
pleasure.
this, yeah, academic session is over. Now I'll request Professor Pratap Rai Chaudhary to have discussion and also feedback session going on, and he'll be chairing that session. Pratap da, are you there?
Yeah, I'm very much here.
Yeah.
Can you hear me? Am I audible?
Yes,
Yeah.
you are audible,
Yes.
Pratap.
Okay,
Yes.
great. Okay, so we come to an end of an exciting 5 days. I think this conference went on remarkably well, given the fact that we were almost at the verge of cancelling it. So it was essentially after a lot of deliberation that we decided to go online. And I think it has, thanks to the spectacular organization of Manoranjan and the SN Bosch team.
I think all of us, I mean.
I think this went much better. This couldn't have gone better in this format. So before this last session is essentially to get feedback from all of you on what you felt about this mode of the conference and any feedback that you'd like to give. Before I ask for feedback, let me just give you some statistics. So we had a total of 294 registered participants. And in several sessions, I saw that there are more than 100 in one session. I couldn't track both the session. So possibly a significant fraction were attending. There were also many people who were attending the live stream. So I think in that sense, this year's QMAT had possibly the highest participation ever at the lowest possible cost. So again, I think it was a very wise decision to have this online meeting. Okay, one of the things that we are contemplating is that, of course, excuse me, is there
Sangeeta, mute.
Okay, so there is of course a limitation in online meeting that we cannot meet each other. We cannot have discussions over tea, coffee, lunch, and especially we cannot go out in the evening for a beer. So there is of course a need for on-site conference where people come and meet. Now, one of the things that we are contemplating is that for the future QMATs, we will adopt a hybrid structure. So we will have on-site participants coming together, but everything will also be at the same time transmitted over Zoom, and people will be able to participate over Zoom. So this gives us the possibility of roping in a much larger section of the community. And also not everyone would be able to travel. And sometimes in the past we have been limited essentially because of limitation of accommodation and infrastructure. So those kind of limitation can be overcome if everyone do not have to specifically come here. Okay. So now at this stage, I would like others to give their feedback on what they felt about this conference and what is their thought about the future.
So may I request everyone to switch on their camera if possible? I mean, if possible. I think now we don't care about the bandwidth and all. So
yeah.
You want to see whether we are there physically or not, huh?
no. It's
Okay,
not. At least
so,
we can have at least we can see all of us.
Yeah, no, I'm joking.
May I request whoever has something to say to raise their hand so that we can have a structured discussion. Yeah,
so Yogesh is maybe. Yeah, Yogesh.
Me?
Oh, Yogesh and Shoykar. Okay, Shoykar, did you raise your hand?
Oh, sorry, I thought whoever is supposed to support you is supposed to raise your hand.
Oh, I
was raising in support of the idea.
I see. Okay. What I was asking is that anyone who wants to say something.
Yeah.
And give the feedback.
Yeah, Yogesh has something to say.
Yeah. Okay, Yogesh, why don't you start?
Yeah, I just want to second what Pratap was saying, that this meeting couldn't have gone better than it has gone. So congratulations to the team. I think that in the future, we can also, because we will have this hybrid kind of thing, we can also maybe advertise it to our international colleagues and friends who may not be able to attend, but they can maybe listen to talks that they are interested in, so that we advertise our work to a wider audience.
Yes, actually, the thing is, in the beginning, when we were planning this meeting, we had planned to have about 5 to 10 international participants.
Okay.
Unfortunately, what happened later on, things got completely into disarray, and we had to quickly put our acts together. That is when that part got somewhat neglected. But yes, in the future, this is something we'll definitely take into account. So we want to have at least some participation of international participants, so that the work that gets presented here gets visibility.
Right. And because there won't be a constraint of travel, I think they will be willing to register and contribute.
Yes, sure. So, absolutely.
Yeah, that's all I had to say.
Okay.
So this very nice QMAT seminar series which you had started, Pratap, that's slightly besides the point, but I think that's also nice to discuss, that one can probably continue with that.
Yeah, actually, see, one of the reasons that it started, we had for quite a while. Then we stopped it because many other things also started coming in. Now that we can maybe think about it separately, of having, let's say, monthly or twice a month colloquium series. But right now, the main feedback that we would like to have is about this conference formats. Arindam, you have to, unmute yourself.
He forgets to unmute.
Are you okay now? Can you hear me?
Yes.
Yeah, we can hear you.
Okay, good. I will take 2 or 3 minutes, so I'll say one by one. At first, congratulations to everybody over there, Manoranjan, Priya, Atin, their whole load, Arti, all the people who have played an instrumental role in getting this conference. It has gone amazingly well. And as Pratap said, 300 people is not a matter of joke. And it shows that the original idea of getting this project, this meeting with what Pratap, Gautam, Rajdeep, Krishnendu had started with and then continued is actually bringing fruits. And we are getting more and more people coming in every year, and we have to do everything possible to make this grow both nationally and internationally. And in that respect, you guys have done an amazing job. Okay. So that's it. There are first 2 or 3 points which I noticed, and that needs to be stopped in the, or needs to be discussed and if possible avoided in the next meeting. First of all, I felt that there are far too many talks from individual groups. Okay, so that is a open point. You can always refute this later. I mean, I'm just giving my observations. What we could do is that in order to, one possibility, I understand we didn't have poster session, and maybe poster session will be one of the possibilities in the next ones onwards, but I felt that if the PI gives a talk, maybe the students, maybe you restrict the number of students, or you give the students higher chance, but maybe from a given group, not more than 1 or 2, for example, can be given. And this will become more and more important in the subsequent years when we have more people coming in into the system. So that's number 1. There are 1 or 2 which could be because of the connectivity issues that, the session changes at short notice, which we should try to avoid. And swapping of the talks should be also avoided. So these are the only 2 or 3 things which I feel that we should keep in mind before we go to the next one. Okay, so this is all actually. I mean, these are the things which I felt noticed, but I understand that it could have been unavoidable from organizers' point of view. Okay, for the next one, for next meeting, okay. We are on the right track. We have increased the participation by a factor of 3 nearly. And we would like to go even higher. Okay, so that means that what Pratap has just said, we should have international participations in a stronger way, because we cannot increase the Indian participation suddenly and dramatically in 1 year, but it will certainly go up, but not in a dramatic way. In order to do so, we need to find ways of reaching out to people through our personal contacts and try and advertise it well ahead of time. And that will probably have to start by early next year or end of this year. So December this year or January next year, we should have to start this. I would also like to suggest in the next edition, a minor amount of registration fee. This is something which we discussed this year, and we remember that, because this was first time in the online mode, we didn't know how people will react, etc. A minor amount of registration fee probably is going to make the seriousness much more. As well as it's something which probably if there are on-site component, we will have to discuss about that financial issues later. With also the fact that hybrid part is important in the next meeting. It means that it needs to be in a place which probably will be able to have both sufficient amount of on-site accommodation and logistics, as well as sufficient amount of infrastructural support to make sure that the online connectivities, everything are intact and dependable. While I personally feel that we should take this conference to as many different places as possible over the course of next few years or so, I believe that we should do this in the next one in a metro city, at least because this will be a brand new model that probably will be tried. We should probably have it in Bombay, or, I mean, this time it happened notionally in Calcutta. It has already happened in Bangalore. It had happened in up north. Maybe Western India needs an opportunity to showcase their infrastructure. We will have to have, and this is something which I was having a discussion with Pratap at some point of time, that we should have to have an online poster presentation mechanism also. and Pratap probably, it was Pratap's idea actually, so it needs to be sought out better so that we can increase a significant number of participations and probably have more talks which are like, in terms of variety of people. And some talks in this conference itself probably could have gone to posters. Okay, so we need to increase the poster and find a way to have poster presentation in the online manner. Right, so that's more or less what I wanted to say. We should involve, more people and see how things go. So we need to have the next, we need to decide who is going to do the next QMAT 4. Right, I'm going to stop here.
Okay, Arindam sir, thank you. I agree to most of the things that you say. For example, I think this time this was a strategic mistake to have too many people from the same group. This actually was something that all the organizing committee, it was a sort of lack of wisdom of the organizing committee and as a whole to sort of select students from groups where PIs were also talking. I think in future we should, since anyway no senior person is talking every year, at most senior people will be talking in alternate years, we should have a strategy that in the years where the PI is not talking, the work should be covered by senior students. So from the same group, having 2 people is maybe okay, more than 2 people definitely makes overlaps. At least, for example, this time I could see that there was some overlap, at least between one talk from my group and mine, which was not really necessary. Manoranjan, you wanted to add something? Manoranjan?
Yeah. So yeah, Pratap, the reason why we have this so many, because initially we had we wanted to have the poster session. Actually, poster session was not able. We are not able to do the poster session, so everything got converted into talks.
Yeah, so this was possibly this year something. It's not anything that has caused a disaster, but I think it's preferable to avoid it. Now, second thing is that having some modalities of having poster session online is something that I will explore. It is possible. It's not impossible to have it.
It is possible. Yeah, it is possible. You have to buy the rooms for it.
Exactly. We have to buy these breakout rooms.
Because you have to buy 10, 15 rooms. Exactly. That will be a little bit expensive.
Precisely. Yeah. So there is a cost involved. So we'll have to have a registration. So this time was absolutely free. Next time we will have to have some nominal registration, which will cover something. Then we can also try to get additional funding from our institutions and so on. But we need.
Can I make a comment here? No, about the poster session. You see, in the real physical, poster sessions where we go and look at the posters, student talk about their work. I mean, essentially, we are investing a dedicated amount of time, let us say one afternoon, and a student is standing there. I mean, in the end, we are investing time in allowing the student to speak up what he or she has done and explain to various people. So I think for the online mode, at least, I don't see any need for poster session, whereas having sessions dedicated for student is fine. For instance, one afternoon could be just again 10 minutes or 15 minutes talk by students, and this is their poster. I mean, after all, in what are they going to show in poster? Some set of calculations, experiment, some discussion. This, somebody will ask a question, somebody would answer it. So let this be a talk-like model, but restricted to 10-15 minutes, or maybe not 15 minutes, even 10 minutes. Each person is going to speak for 10 minutes.
No,
and
Vijay will not be able to handle it. Just multiply, say there are
hundreds of
posters.
No, so the selectivity may come. I mean, one doesn't have to necessarily go like the conventional poster model that everybody has to have a poster. So some sort of screening can be done. But what I'm saying is, what else do we expect from a poster session?
Yeah, what Brijesh is saying has a point, but so we have to accommodate the number. So making it very selective is not going to work. Means there are students who are star students, there are students, but all of them want some exposure of their work.
No, by screening, I did not mean selectivity. By all I meant was from each group nominates one person or two persons, or maybe even reduce the time. Why give 15 or 10 minutes? Give 5 minutes where they just introduce the problem and the key points.
Yeah, I think that is one possibility. Personally, I don't like very short talks, but that is definitely a point of view that I respect. There is another possibility. If we don't want poster session, is that okay? In a poster session, at least for me, when I go to a big conference, I don't see all the posters.
That's right.
I see only posters that interest me. So, for example, I will go to maybe magnetism posters and superconductivity posters primarily. Then, if most of the time when I start discussing 3-4 posters in depth, the time is up. So maybe at the most 7-8 posters is what I can cover at least. So one possibility is that for students have a session like what Brijesh is saying, but have instead of 2 parallel sessions, have let's say
more parallel sessions. Yeah, that's correct. That's a better strategy.
So then
you can just have a list of or you can just have a list of posters, meaning in the sense the students can just solicit discussions. So you can have like 50 topics with students' names even at the beginning of the conference. And on one-to-one basis, they can actually fix appointments and solicit discussions. These are students who are soliciting discussions. And then they can fix appointments to individuals because posters are more of an individual discussion. So that's also a possibility.
But I think what Pratap is saying is good. Have short presentations, but many parallel sessions of students. So that, and they can be thematically grouped. You know, magnetism, superconductivity, quantum optics, or whatever, cold atoms, etc. So you have many parallel sessions. And if I want to listen to these 5 posters, I sit there in that session. Somebody else can do the same thing in some other session. But after all, yeah. So I think that seems like a good overall model.
Yeah. So I think there are these various models, and these models send us please the input in a structured format. We will definitely discuss the next before the next meeting. We will definitely discuss this in detail. But the bottom line is that we will have to have a modality as the alternative to posters. So whether it is posters or whether it is short talks with many parallel sessions, or whether it is like what Bhavtosh says that there are some topics listed and they take appointments. So those things we can flesh it out, but we will have the mechanism to accommodate a large number.
Yes, one more comment I had to make, which I should have made earlier. You see, people are talking about hybrid model. Of course, the present circumstances have forced upon us the the online mode. Now, but if you think of it otherwise, it looks like a good model where the travel constraints, teaching constraints, semester constraints, or even family constraints, everything are sort of automatically taken care, and a large participation is assured. Of course, in any session at any time, you would not have 100 people. You may still have 50 people, but overall there are about 300 or 200, whatever number of people who are logged in, randomly or selectively looking at talks and listening to them. So why not just say, okay, let us adopt from time today the online model? I mean, what is completely wrong with that?
And you mean that completely online model?
Yeah. I mean, this allows all kinds of flexibilities. No last moment cancellations. Speakers cannot give an excuse. Okay, I could not come, so please find another.
For me, the fun is actually outside the conference. More than half the fun is actually outside the conference.
No, but I'm talking about conference, not the fun part of the conference.
But I think the fun part is the part, right?
So the point is this: what Brijesh, what you are saying is absolutely right, and the hybrid model. When I'm saying hybrid model, let me explain what it is. every talk you can attend either online or offline, and every presenter can present either online or offline. So for example, in our institute, in TIFR, all our lecture rooms are fully equipped that if there is someone giving a physical talk, that can be transmitted on Zoom. So you can see that on Zoom, just like we are seeing here. So anyone who has a constraint will have the possibility of not coming and attending the entire session online. However, if some
but then that guy will feel he is missing the fun part of it.
if you want fun, you have to come.
That you cannot assure, right?
So I want to have a clear model, no tentativeness is in mind. you go for it or you don't go for it.
But Brijesh, I don't think there is any tentativeness in this. You clearly say whether you are coming or not coming. If you are not coming, you go for the online and you are attending the conference exactly the way everybody.
So also, there is another factor that my personal suspicion is that once we give people the opportunity to attend it online, then most people will be online.
And that is true.
How many people really want to travel for 5 days? And means you have your own work and so on. So, in fact, earlier always the QMAT was 3 days because 5 days no one would be staying. You would have an empty room at the end.
That is true.
Can I add a point, Pratap, on this?
Yes.
Yeah. So to what Brijesh is saying, actually, it needs some consideration. Actually, Manoranjan, Priya, and Athena and group have done so well. And every day we are learning new technology. I mean, the whole idea of booking tickets, paying, getting money to bring them, particularly if you are wanting more international participation. So it is not such a bad idea from the academic content point of view. We are not severely compromised if it is done purely in the online mode. And as we see it, I mean, whether it is COVID or some other reasons, the funding scenario is not going to be very flexible over the next 2-3 years. So if we can survive with Machar Jhol and little bit of, so I think it is perfectly fine that it is held, at least the next one, completely in the online mode, particularly if the decision is to have more international participation and getting the real stellar people, get their talks, it will be much, much easier. So that's my submission, that making it fully online, at least for the next 1 or 2 years, would not be such a bad idea.
So the point is making it fully online for the organizer is actually better because it reduces the work.
No, for the participant also. For the, I mean,
And funding is an important factor. I mean, I didn't say it, but it's a very important factor sometime or many times. So many things will be sorted out, whereas the academic activity goes on forever, as long as, of course, there is internet and Zoom and whatever else.
So one of the thing is, okay, this is something we can decide essentially by what the community by and large. So we are expressing our opinion, but we'll ask for, so if there are things that are very divergent in opinion, we'll ask for a poll. Manoranjan, I hope that all these 294 this time you have registered, we have an email address for them. We have an email list.
Yeah, we have more than that actually.
Okay.
Pratap, can I comment on what you just said? Yeah. I think what Brijesh and Satyabrata was saying are perfectly fine. I mean, what's important to be understood here is that if you don't wish to come, you don't have to come. And you do not have to travel. And you will have exactly the same access to all the academic material of the conference anyway. So it's what we would like to not miss out, and this is why the hybrid model is at least being thought of here, is that this purely online mode does reduce the interaction at the level of physically seeing each other. Because, and that is, to be honest with you, is a problem. After the sessions, during the tea, you just don't meet anybody, right? You go and have tea yourself here. And that's so much of academic discussion happen at that point of time in any conference.
That is true.
Right. So I think at the end, this should be left to the organizers, because as Pratap just said, that it is primarily the headache of the organizers to have it anything on site. So if the organizers believe that they will be able to handle something, I think why do we want to? And as long as people who are not traveling, those who want to access in the online mode, do not miss out any of the academic program, I can't see an obvious problem in hybrid.
Yeah, here I want to add something.
As you said, because of funding, because of COVID and so on, in the next 1 or 2 years, I don't expect too many people wanting to come. But some people might want to come.
Yeah.
And those who will want to come, I think if we can make arrangement, that it would be reasonably good. Manu, you wanted to say something?
Yeah, Pratap, I want to point out here, which I also felt that it should have been there. See, we should buy from next conference, we should buy at least 10 rooms where, suppose if someone wants to have a discussion in some particular topic, they can go to the room, they can ask the organizer and say that, okay, I want to have a discussion session, and then they can move. Even then, there are parallel talks going on. Maybe not everyone is interested in that talk, and they can go to that room, which I think should have been there. Earlier, we didn't realize. I think next meeting we should have that at least 5 or 6 or maybe 10 rooms like booked.
Okay, so this is something that we can definitely do. This time we did not go all the way because we did not know how it will pan out. But since it's going well, next time we can have the breakout rooms. So, are there other feedback? Okay, let me in between make one announcement. So, this is something that I have discussed with some of the organizers this year, Manoranjan or Indam, that next year Bombay would like to host the conference, whether it is eventually, if it is online, then it is virtually hosting, but otherwise, if it is hybrid, then it is partly hosting here and online. So Bombay means this is something I have discussed with my colleague Rajdeep Sen Sharma, and we are both quite enthusiastic and willing to take up the responsibility for next year's organization. We will possibly rope in some of the other institutes in Bombay, maybe IIT, maybe CBS, where we have condensed matter colleagues. And if the decision eventually is go for hybrid, then we'll, for example, need some infrastructure, some rooms for accommodation and so on. So we'll arrange that. So if there is no objection, then we will organize it next year.
Fantastic.
That's great, yeah.
Okay, so any other feedback? Okay, feel free, of course, to give the feedbacks on email, and we'll specifically ask for feedback also. So if you don't have if you haven't thought of it now, you can always write to us.
Maybe
it's a community meeting, and we would really like people to consider this their own meeting. Yeah. So your feedback is valuable. It's something that the community should shape. Yes, Brijesh.
No, I was just suggesting a way to get feedback. I mean, apart from, okay, anybody can write his or her views to you, but I'm saying since, as a point of reference, you and others, whoever have taken the responsibility to host this next year, you can maybe write 5 questions which you feel are important to be decided upon. And then it's like a feedback form and just circulate to 300 emails.
All right. So what I will
because that makes the feedback very specific, and it sort of focuses on what the organizers feel should be the way in which it should be held, or something like that.
Very good. That's an excellent suggestion.
Otherwise, it becomes a vague feedback. Everybody is speaking out something, and we don't know what is correct, what is not correct.
Exactly. So what I will do is I will send a Google form to everyone.
Yeah, that would be very good.
Google form, and then we'll have the feedback.
That would be fantastic. It would be easy to keep for you also.
Yeah. So I'll send out the Google form, and I'll coordinate that with Manu. And
yeah.
Okay, is there anything else? So Google form is down.
Nothing but to congratulate the organizers once more and on a very well done job.
That is true.
Yeah.
All right, great. So I
it's-
think now we formally close the conference.
Yeah, I mean,
maybe he
I'll
has a
have
vote of
just
thanks
vote
to
of
make.
thanks.
Yeah, so
I'll-
the vote of thanks essentially is to the organizers and other than the Manoranjan, who are the other ones who helped behind the scene. Manoranjan, you have to
so
specifically mention some people.
yeah. So if you want to, if you allow me, I'll just read some of the names.
Yeah.
Okay. So, okay. Good afternoon, everyone. Dear speakers, chairman, chairpersons, and participants. It's my honor and privilege to deliver the vote of thanks on behalf of organizing committee. First of all, we extend our heartfelt gratitude to all the speakers for sharing your important works and idea with us. We also thank our chairpersons for conducting the session smoothly. And also, we thank all the participants for their active participation. Besides, we also thank each and every one of you for joining the meeting in such a difficult time and making it a success. Next, we like to thank our funding agency, Journal of Physics Condensed Matter IOP Publishing House. Krishnendu convinced them to give us some money, so they gave it. And other funding came from IC Bangalore. Thanks to Arindam Da and Anindya Da for giving that money.
Karan, can you
And
call me in about 10 minutes?
the whole, okay.
Yeah, go ahead.
So I'll next thanks Professor Priya Mahadevan and Professor Aarti Garg for finalizing the program schedule. Actually, it was done by both of them. And then I should thank the administration of SN Bose Center. They're very helpful and thank you for them. Thanks to them. I'll especially thank Sanjay, head of our computer center. He took real personally interest in this thing and he made sure that everything runs smoothly. And his team, Devalina, Bapi, Sagar, for handling the whole event on the Zoom. And I also want to thank volunteers, Joy, Sudeep, Mona Lisa, Devasmita, Sanyur, Monadeep, Somasri, Mona Lisa Chatterjee, Jyotirmay, Kaushik, Suraka, and all the emails and program schedule was taken care by the Sudeep and Joy, especially thanks to them. And last but not least, I personally thank all the organizing members, Atin Pal, Priya, Setti, and India Da, Arindam Da, Aarti Di, Guptos, Gautam, Krishnendu Da, and Pratap Da, and Rajdeep for their wonderful help and their kind cooperation, without which this event would have not been possible. And thank you again. Pratap Da.
Okay. All right.
You can conclude,
so let's give this virtual clap to all these who organized. I can see some virtual clap coming up.
Some real ones.
Some real ones as well. Okay. So I think we'll sign off here and officially close the conference.
Okay. Thank
you, everyone.
See you again next year.
Bye. Bye.
Bye.
Bye.